Testing 1, 2.
Till your will be done, we will fight for your kingdom come. We will raise your banner high as one. This is our battle cry. We will shout claiming victory. We will stomp on the enemy. We will sing as one with your anthem song. This is our battle cry. This is our battle cry. We will fix our eyes into your sun. We will run into the races won. We will find our strength in your secret place. This is our battle cry. This is our battle cry. We will not entangle ourselves in this world. We'll live to praise the Lord. We will not entangle ourselves in this world. We'll live to praise the Lord. We will not entangle ourselves in this world. We'll live to praise strength of your love. This is our battle cry. This is our battle cry. This is our battle cry. Cold out of darkness, now I'm walking in your light. Reached out to save me, you are on my side. Fear and anxiety, they have no hold on me, so I won't be shaken. I've got the God of peace in me. I got joy, and it's filling up my heart. You gave me a brand new start, with new mercies every morning. I got peace, no one can understand, and the world can't comprehend. It's only by your love. I've got joy. I have been chosen. Heard you calling out my name when I feel hopeless. You remind me again of all your promises, how you're holding on to me, so I won't be shaken. 'Cause I know your grace has set me free. I got joy, and it's filling up my heart. You gave me a brand new start, with new mercies every morning. I got peace, no one can understand, and the world can't comprehend. It's only by your love. I've got joy. I've got joy. Called out of darkness, now I'm walking in your light. Reached out to save me, you are on my side. I got joy, and it's filling up my heart. You gave me a brand new start, with new mercies every morning. I got peace, no one can understand, and the world can't comprehend. It's only by your love, by your love. I've got joy. Oh, I've got joy. You know I've got joy.
The same God who spoke all space and life to be is the God whose voice speaks inside of me.
Well, good morning, everyone. Good morning, everyone. How's this for a Monday morning, huh? Well, we have a very special Christian scientist who's going to talk to everyone about creation, about scientific facts. And so let's welcome Dr. Jason Lisle.
All right, well, it's good to be with you this morning. My area of expertise in science is astronomy, okay, astrophysics. So I study the universe, and that's pretty neat. So what I wanted to do today is talk about our solar system, The planets, the sun, and everything that orbits the sun basically is the solar system. And one of the cool things about the world we live in today is we've actually sent little spacecraft out to all the large objects in our solar system and a number of the small ones too. So we know what all the planets look like up close, and that's pretty amazing because that's something that, our great-grandparents could only have imagined. They could see the planets with a telescope, you can see them a little bit, but we've actually sent spacecraft out and visited all these worlds. So that's pretty amazing. This is what the solar system would look like if you could look at it over the North Pole, and you can see the orbits of the planets there. We've highlighted those orbits. And this is where the planets are right now. So that's what it actually looks like at the moment. Now, if I speed up time, the planets orbit the sun like that. They orbit counterclockwise if you're looking over the North Pole of the solar system. And you can see Mercury orbits pretty quick. It takes only 88 days to orbit the sun once. Venus takes a little longer. Earth takes 1 year. That's where we get the idea of a year. That's how long it takes the Earth to orbit the sun once. Mars takes about 1.5 years. And so there you go. And because you might notice right now that Earth and Mars are really close together. You see that? They'll be even a little closer in the next few weeks, apparently. And that happens every 2.1 years. Every 2.1 years, Earth passes Mars. And when it does, Mars, because it looks so close, it looks very bright. And so that bright red star that you see in the east, you might have noticed that the last few nights, that's Mars. So you can actually see that with your eyes. Pretty neat. Now, the outer planets, they're much further away from the sun. See that? Yeah. And so if we speed up time, so the inner planets are orbiting, and then the outer planets, they're just barely moving. We really have to speed up time. See, the inner planets are really whipping around there. And then that gets Jupiter and Saturn to orbit. Jupiter takes 12 years to orbit the sun once. Saturn takes 29 years to orbit the sun once. And it's pretty amazing. Pluto takes 248 years to orbit the sun once. So that's what it looks like. Now, a lot of times you'll see the solar system overhead like that, but we can also tilt it, and the solar system, all the planets are kind of in the same plane. You can see there's a few small differences, but they're all in the same plane, and we're going to find that's a design feature. That's so that they don't collide or anything like that, because if they were all different directions, especially when there's not a lot of space available, that would be unstable. Sometimes in textbooks, you'll see the solar system kind of at an angle like that. And sometimes people mistakenly think that's an overhead view, and the orbits are really squashed. They're not. They're almost a perfect circle, but not quite. They're just slightly elliptical. That's a slightly squashed circle. So, the person who discovered that planets look like that and orbit like that was Johannes Kepler, and he was a Christian. He was a Christian astronomer like myself. And he discovered that you know how the Mercury orbits real quick and then the other planets are slower? He discovered the exact mathematical formula for that. He discovered that the period of a planet in years squared, that's multiplied by itself, is equal to the distance from the sun cubed in AUs, and that's pretty neat. So he was able to discover that by looking at a list of numbers recorded by Tycho Brahe. So creationists have made some remarkable strides in science. Kepler also figured out that planets, when they're a little closer to the sun, like Mercury, see how it's farther away there, and it's a little closer there. When Mercury's closer to the sun, it speeds up, and when it's farther away, it slows down. So it kind of does that. And Kepler discovered the exact mathematical formula for that as well. So pretty neat. And he was a Christian and a biblical creationist. He believed that God created in 6 days a few thousand years ago, just as I believe, because that's what the Bible says. So because we've sent spacecraft to all these planets, we know what they look like now. And, the secularists, those who hate the Lord and they want you to not believe the Bible, they try to tell you that the solar system formed 4.5 billion years ago as a nebula collapsed and the planets just kind of formed from gas and so on. But there's a lot of evidence that that is not true and that the universe is exactly the way the Bible says it is and the way God created it to be. And so we're going to take a look at these planets and many of their moons, and we'll take a look at that today. But we're going to start with the sun, because the sun is, most of the mass of the solar system is in the sun. 99.98% the mass of everything is in the sun, in our solar system. So that's what it looks like. The sun is 100 times larger than the Earth in terms of its diameter. So if it looks really small, that's because it's 93 million miles away. And the sun is basically a stable hydrogen bomb. It's fusing hydrogen into helium in the core, and that releases energy, and that's what gives the sun its power source. And it's got plenty of fuel there to last longer than you're going to have to worry about it. Let's put it that way. And this fusion process is really efficient. The sun actually gives off more energy in 1 second than 1 billion cities on the earth could use in an entire year. So it just reminds us that God has unlimited power. And God made this as the light to rule the day. You might notice that there are some little black spots on the sun. We call those sunspots because we're not very creative apparently. But that's what they are. They're sunspots. And those are regions on the sun that are a little bit cooler. The surface of the sun is normally about 6,000 degrees Celsius, pretty toasty. And those sunspots are a chilly 4,000 degrees. So they're a little bit cooler, which is why they're not as bright. And they're caused by magnetic fields. The sun has lots of magnetic energy, and that causes those sunspots. So that's what I got to study when I was in grad school. I studied the sun and how things move on the surface of the sun. It's basically a ball of gas, though, so everything can move and move around, and that gas is held together by its own gravity. Yes, gas has gravity. You get enough of it, it'll form a sphere. So that's the sun. And that anchors all the planets. They all orbit the sun because the sun has most of the mass. So we're going to take a look at the planets now. Let's go out to Mercury, the closest planet to the sun. There's little Mercury. Look at that. It looks kind of like the moon, doesn't it? Yeah, Mercury's about 1/3 the size of the Earth, and it's 3 times closer to the sun, so it makes that easy to remember. And it takes 88 days to orbit the sun once, but it rotates really slowly. It takes 58 days for it to rotate once. So very slow sunrises and slow sunsets and so on. So it's just kind of a heavily cratered world, and that's because Mercury doesn't have much of an atmosphere. It's kind of, again, like Earth's moon. It doesn't have much of an atmosphere either. And so anything that comes close to Mercury, any other rocks in space, because there's lots of rocks that are orbiting the sun, asteroids, if any of them come close to Mercury, its gravity pulls them in and they hit it, and that makes one of those craters. And so this is what the Earth would look like if God hadn't provided us with this wonderful atmosphere that protects us from those things. Because when asteroids come into Earth's atmosphere, they burn up, and that protects us from it. Most of them do. 1 in a billion makes it through, but that's not a lot. So there you go. So that's Mercury. And one of the things that was really surprising to scientists, those scientists who reject the Bible, is that Mercury has a magnetic field like the Earth does. So your compass would work on Mercury. It would point north. And whenever you have a magnetic field, that means that there is electrical current going on inside the planet. And electrical current, like a battery, runs down with time. Okay, so you know how batteries eventually run out and you have to replace them. Well, there's no replacement for Mercury's battery, and so the fact that its battery is still going tells us that this little planet cannot be billions of years old, or that magnetic field would be gone by now. It would have run down. And so it's kind of like if you had a toy that has batteries in it and it's running, you figure, well, somebody put the batteries in there pretty recently, otherwise it would be dead by now. So that's an indication that Mercury's nowhere near billions of years old. You couldn't survive on Mercury, though, because it has no atmosphere. The day side, because it's close to the sun and there's no atmosphere, the day side gets up to 800 degrees Fahrenheit. Pretty nasty. And then the night side, actually, the night side can drop to several hundred degrees below zero, a couple hundred degrees below zero. And so you'd freeze on the night side and you'd burn to death on the day side. So apparently the best place to land on Mercury is kind of right in the middle, right in between day and night, right just before sunrise. And then the temperature would be pretty nice, I suppose. You'd have to have a spacesuit, though, because there's no air on Mercury. And it turns out Mercury rotates so slowly that if you landed on a place that's just before sunrise and started running west, you could actually outrun sunrise. You could actually stay in the night side. And you don't dare stop, though, because then the planet will rotate around and you bring you into the day side, and then you're toast, literally. Okay, so there's Mercury. We've sent a couple spacecraft past Mercury, and so we know that's what it looks like, and we know about its magnetic field. Now, the next planet out is Venus. Venus has been called Earth's sister planet because it's about the same size as the Earth. Just slightly smaller. It's about 95% the size of the Earth. But it looks really very different from the Earth, doesn't it? It looks kind of bland, and that's because it's completely covered in thick clouds. You'd never see the sun If you lived on Venus, you'd never see the sun. It'd be permanently overcast, which would be really depressing. But that would be the least of your problems. So here's Venus, and when you look at it in a telescope, it always looks kind of bland like that. You can never see the surface of it because of those thick clouds. Venus has a really thick atmosphere, 100 times as more atmosphere than the Earth has. And so that would be a problem. And that thick atmosphere traps in solar energy from the sun, and that makes the surface temperature of Venus 900 degrees Fahrenheit. That's enough to melt lead. So that's going to be an issue. We've sent several spacecraft to Venus. The Russians really liked Venus, and they sent a number of spacecraft to land on Venus. And those spacecraft landed, and they worked for a little while, and then they stopped working because they basically roasted in Venus's hot temperatures. So because Venus has all that atmosphere, it's actually hotter than Mercury, even though it's further away from the sun. That's kind of surprising. And you'll hear people say, well, if we're not careful, Earth will end up like that, right? If we put all this carbon dioxide out. No, Venus has 100 times more atmosphere than Earth. This could never happen on the Earth. So, well, one of the spacecraft we sent around that went into orbit around Venus is called the Magellan spacecraft. And the Magellan spacecraft had a radar on it, and radar can go right through clouds. And so we were able to map the surface of Venus using radar, and so we know what the surface looks like now, and it looks like that. So that's what Venus would look like if it didn't have any clouds. Now, it never looks that way from Earth, because we always see the clouds, but if you use radar, you can penetrate those clouds. And so it's got a really interesting surface there. But yeah, so in the past, there were some secularists that thought Venus might have all kinds of exotic life forms on its surface, because they figure life evolved on Earth, so it probably evolved elsewhere. And you'll see that in the older science fiction movies. I still remember seeing in Outer Limits with William Shatner landing on Venus, and it's all eerie and everything. But that was before they learned that the surface temperature is 900 degrees Fahrenheit, so you're not going to have life there. And that atmosphere is made up of carbon dioxide, which you can't breathe, and the clouds are made up of sulfuric acid type compounds. Furthermore, the atmospheric pressure would crush you like a tin can. So don't go there, okay? And some people ask, well, why would God make a planet like that with a poisonous atmosphere and a surface temperature 900 degrees? Well, you're not supposed to go there, right? He didn't make it as a vacation spot. He made it to be beautiful, and it is beautiful. Those clouds are highly reflective, and they make Venus the third brightest object in Earth's sky. You got the sun, the moon, Venus. Pretty neat. And the other thing that's interesting about Venus is it rotates backwards. It just the opposite way of the Earth. So the sun would appear to rise in the west and set in the east on Venus, the opposite of the Earth, although you'd never see it because of those thick clouds. So, and that is contrary to what the secularists expect, because they think that our solar system, they don't think it was created by God. They think it just collapsed from a cloud in space, and all the planets formed. And if that were so, the planets all ought to be rotating the same way, and they all ought to be upright. And Venus is just exactly the opposite of what the secularists were expecting. And I think it's neat when God does stuff like that. I think he did it just to confuse the secularists. So there's our sister planet. Not really much of a sister planet, because you would die there very quickly. Okay, so the next planet out is Earth. It has the best restaurants of any planet. All my friends live there. All your friends live there. So there you go. So there's Earth. Yeah, isn't it just beautiful? And we live I feel very privileged that we live in a time where we've seen our planet from above. That's something that our great-great-grandparents could only have imagined that, but we get to see it. In fact, a friend of mine, he's actually an astronaut, and he's spent a lot of time on the International Space Station. It orbits about 200 miles above the Earth, and when he has downtime, he goes to there's kind of a window in the lower section of the International Space Station, and he looks at the Earth and takes pictures of it, and it's really beautiful. He shared some of those pictures with me, and they're quite lovely. So Earth has all kinds of properties that make it just right for life, and that's what the Bible tells us. In Isaiah 45:18, the Bible says that God formed the Earth to be inhabited. He designed it for living creatures and human beings to be able to survive there. And so Earth has an atmosphere with nitrogen and oxygen. Oxygen you need to breathe, obviously. And the Lord made the Earth to have all kinds of liquid water on its surface. And of course, we need water to live as well. And he put the earth at the right distance from the sun so that we wouldn't, freeze to death for being too far away or burn to death for being too close. It's just at that right distance. And he tilted the earth 23.5 degrees so that we would have seasons. You don't have too much of seasons in California, but everywhere else you do. So there you go. And that actually increases the range of habitability on the earth. So really beautiful, beautiful planet. We think that the earth, we think before the Great Flood, we think all the continents were connected together. Want to see that? Let's see if I can get the map here. So maybe something like this is the way it looked before the flood, where the continents are all kind of together and look kind of different than it does today, doesn't it? And then during the flood, we think God used plate tectonics to push apart those continents, and that caused the flood, and it also ended the flood. And so this is what the earth looks like today. So very beautiful. The earth has polar ice caps, and they shrink in summer, and then they grow in winter. Of course, summer in the northern hemisphere is winter in the southern hemisphere, so they shrink and grow. And it rotates in about 24 hours, which is why we have our day. So that's how that works. Mountains, valleys, canyons, a lot of beauty on this planet, and very, very colorful too. So the earth has one large moon, which we call the moon, because we're not very creative, I guess. Actually, this, for a long time, we thought the moon was the only one. It wasn't until the year 1610 that Galileo discovered that other planets can have moons too. He discovered that Jupiter has moons. Earth has just one moon. Here's what it looks like. And it always looks kind of like that from the earth, because the moon rotates at the same rate it revolves around the earth, and so we always see the same side. It wasn't until when would it have been? Late 50s, early 60s, that we were able to send spacecraft out to the other side of the moon to see what it looks like. The moon does rotate, though. It's just because we're stuck on Earth, and it always keeps the same face pointed toward the Earth, we always see the same side. But if you were to watch the moon from space, you'd see it does rotate, and you could see what the other side looks like. The other side looks quite a bit different from the near side. It's actually quite a bit brighter. It doesn't have those large dark features called Maria. There you can see the Earth in the background. Isn't that beautiful? I've always been a little bit envious of the astronauts who got to walk on the moon back in the late 60s, and we're going to do that again here in a few years, hopefully. So wouldn't that be neat to stand on the moon and look up and see the Earth up there, look like this little marble, and knowing that all your friends live there, and it really shows you just how small we are compared to all that the Lord has created. And maybe he did it that way to give us a little bit of humility, so we'd recognize that we're not the most impressive thing out there. God is the most impressive thing out there. The moon has what's called remnant magnetism, and that means that there's little bits of magnetic field, but your compass would point different directions depending on where you're at. It doesn't have like a north and a south pole. So, and that is an indication that the moon cannot be billions of years old, because that remnant magnetism would have decayed away, and so you wouldn't have that anymore. Also, the moon, did you know the moon is actually moving away from the Earth about 1.5 inches every year? It gets a little further away. And if you wanted to find out why that happens, you'd have to go into physics and learn about physics and tidal effects. But that's another indication that the Earth and the moon can't be billions of years old, because if you run the equation backwards, and the speed is not constant, it would actually get faster as you go back into the past. The Earth and the moon would have been in the same place 1.4 billion years ago. And that may sound like a lot, but the secularists believe the Earth and moon are 4.5 billion years old. But you see, they can't be older than 1.4 billion just based on the rate at which the moon's moving away. Now, we would say they're only about 6,000 years old, and the moon has only moved away from the Earth by about 750 feet since creation, so less than a mile, not a huge difference. So really pretty amazing. So that's my favorite planet. I would not want to live anywhere else, because you'd die. But there you go. So that's Earth. Now the next planet out is Mars. And even though Venus has been called Earth's sister planet because they're about the same size, Mars is probably the most Earth-like planet other than Earth itself. And so there's what Mars looks like. Actually, I think I have a better surface image of it here. There we go. So that's what Mars looks like. It's the red planet. It's that bright star you see over in the east in the evening sky. And you'll see that for several more months, and then it'll get fainter and fainter as Earth moves away from Mars. So that's what it looks like. It's the red planet because it's made up of all kinds of iron compounds, kind of like rust. You know how rust looks red? That's kind of what Mars is made of, really, is rust. So there you go. And it has some darker regions on it, some lighter regions. You can see that there. Mars is similar to the Earth in a number of ways. It has features like the Earth has. It has mountains. It has valleys. It has canyons like the Earth does. It doesn't have any water, though. So that'd be a problem. Nothing to drink on Mars. And it has a real thin atmosphere of carbon dioxide, which you cannot breathe. So you would not be able to breathe on Mars. That would be a problem too. But Mars has polar ice caps like the Earth does. You see the northern polar ice cap there? Yeah. And now it's made of a different kind of ice. It's made of dry ice, which is frozen carbon dioxide. But it shrinks in the summer and it grows in the winter, just like the polar caps on the Earth. So Mars has a lot of features like the Earth. It has canyons, in fact. In fact, if we rotate it around here, you see that this large feature right here? That's an enormous canyon. It's called Valles Marineris. It's probably the largest known canyon, way bigger than Earth's Grand Canyon. In fact, that's about as long as the United States is. So it's massive. And then there are mountains on Mars too, volcanoes. You see these three, it looks almost like there are three pimples there in a row. Those are volcanoes. And then you got a really big one here that's called Olympus Mons. That's the largest known volcano. It's 3 times taller than Mount Everest. It's massive. But it's shallow sloping. The base of that thing would cover the entire state of Iowa. So pretty neat. So it's got a lot of stuff like the Earth, and it rotates about the same rate as the Earth does. Earth takes about 24 hours to rotate. Mars takes 24 hours and 37 minutes, which I think is cool because that means you could sleep in an extra half an hour every morning. And it would never catch up with you. So I could do that. Mars is tilted about the same as the Earth, so it would have seasons, summer and winter, but the overall temperature would be much colder. Occasionally the temperature will get up to 70 degrees. That's not so bad, but it can drop to several hundred degrees below zero, so that is bad. So there we go. Mars has 2 moons, and they're tiny. They're called Phobos and Deimos. Those names mean fear and terror, but that's because Mars is named after a pagan god, the supposed god of war, and what accompanies war but fear and terror. So it's 2 moons. Let's take a look at the outermost, Deimos. Deimos is less than 10 miles across. It's a small moon, and it's not quite round. A lot of people, that surprises people. They think that all moons are round, but Deimos isn't. Yeah, it looks like a potato, doesn't it? Isn't that wild? Really small moons tend to have kind of a random shape because there's not enough gravity to pull them into a spherical shape. So there's little Deimos. You can see it in a reasonably powerful telescope. I've seen Deimos orbiting around Mars there. Now, Phobos is a little bigger, and it's really close to Mars. Phobos orbits closer than any other moon to its planet. So there's Phobos, also not quite round. Got a massive crater on one side. Really pretty neat. It's just a little more than 10 miles in diameter, and you could just imagine the view of Mars if you were standing on Phobos and looking up, seeing Mars, because it orbits so close. It would be spectacular. Now, the gravity on Phobos is really weak because the bigger a planet or moon is, the more gravity it has. Phobos is only a few miles across, so the gravity is very weak. You could jump really high on Phobos. In fact, you could pick up a rock and throw it into orbit. You can actually watch the rock go over the horizon, and you could catch it when it comes back up on the other side. You could play catch with yourself. So it's kind of weird to think of these situations that don't really happen on Earth. So Phobos and Deimos, the 2 moons of Mars. Mars has remnant magnetism like the moon does. And that indicates that it cannot be billions of years old because magnetic fields decay with time. They get weaker and weaker, and we would expect that. So Mars can't be billions of years old either. Now, these first 4 planets that we've looked at, Mercury, Venus, Earth, Mars, they're called terrestrial. That means Earth-like, in the sense that they're rocky worlds. You could land on them, get out and walk. I mean, you'd have to have a spacesuit, but you could land on them and get out and walk and so on. The planets we're going to look at now are not terrestrial. Jupiter, you can't land on Jupiter because there's no solid surface to land on. It's made of gas. And so let's take a look at Jupiter here. And Saturn's the same way. They're basically balls of gas that are held together by their own gravity. Now, gas in space tends to spread out unless it's already in a sphere, and then its own gravity will hold it together. So there's Jupiter. It's a beautiful planet. Jupiter's about 10 times larger than the Earth. So just imagine lining up 10 Earths across the equator there. That gives you a feel for how big this world is. It's got these features, those stripes that you see, those are clouds that circle around Jupiter. Jupiter rotates very quickly. It takes only 10 hours for it to rotate. And so its clouds tend to stretch into these different features. And because they're made of different stuff than Earth's clouds, they get different colors. I mean, you have some white like Earth's clouds, but you also have a lot of orange. And that comes from chemicals like methane and ammonia that are in Jupiter's atmosphere. You can see it rotating around there. And it's kind of like jet streams on the Earth. If you ever heard of jet streams, Earth has several zones where the weather goes a certain way. Jupiter's bigger, so it has more of them. And they're colored, so you can actually see them, which is quite neat. And you can usually see these even in a small backyard telescope. You can see at least the two main ones there, the two really dark ones. So those are the two equatorial belts, and they're almost always visible in a small telescope. The dark ones are called belts, the light ones are called zones. So Jupiter has belts and zones. It also has this great red spot, which astronomers call the Great Red Spot. And it is basically a giant hurricane. It's a high pressure system and it rotates. It's like a big storm on the Earth. You could put 2 Earths right in there. That's how big it is. Now, hurricanes on the Earth, they're powered by the temperature of the ocean. Hurricanes actually cause the ocean temperature to drop a little bit after they move past. And then the hurricanes move over the land and they get cut off from their power source and they kind of disappear. But Jupiter doesn't have any land. So that hurricane just keeps going. We know that hurricane has been there for at least 300 years since we've had telescopes powerful enough to see it. It might have been there since creation, for all we know. So there are other storms that develop on Jupiter, and some of them can collide into each other and either add or subtract depending on their nature. But the red spot appears to be pretty stable. Now, Jupiter has 2 features that demonstrate it can't be anywhere near billions of years old. One, it has internal heat. Jupiter actually gives off twice as much energy as it receives from the sun. So it's getting 1 unit of energy from the sun, gives away 2. Takes in 1, gives away 2, kind of like our federal government, okay? Now, it can't do that forever because eventually it's going to run out of energy, okay? And so that's an indication that Jupiter is a few thousand years old. Have you ever taken a potato out of the microwave and it's nice and warm? You can feel the heat coming off of it, right? Now, if you just let it sit there and you come back 2 hours later, do you still feel heat coming off of it? No, not after 2 hours because it's all cold by now. It's the heat that's gone into space. Jupiter's like that, but it's a much bigger potato. So it can do that for a few thousand years, and it's not a problem. But it can't do it for millions of years. Occasionally see a black spot on Jupiter. That's the shadow of one of its moons. And you can see that in a small telescope. If you actually predict when they're going to happen using computer software, like this software here. And so that's a moon casting its shadow on Jupiter, and that's the moon Io. And we're going to take a look at Io here. Jupiter has a number of moons, 4 big ones that were discovered in the year 1610. That was the first time that we had telescopes powerful enough to see them. I love Io. It's my favorite moon because it looks like a pizza. Isn't that neat? Wild. And so it orbits around Jupiter. It keeps the same face pointed towards Jupiter, just like our moon does. All large moons do that. But it looks totally weird. It looks kind of yellow and orange, and it's got all these weird features on it. And those little spots that you see on Io, those are volcanoes. Io is the most volcanically active world in the solar system. It's got all kinds of internal heat, and that might suggest that it's not anywhere near billions of years old. So in fact, the surface of Io has been completely resurfaced by its own magma from volcanoes. When Voyager 2, it's one of the spacecraft that flew past Jupiter, flew past Io. When Voyager 2 flew past Io, it discovered 9 volcanoes going off at the same time. So pretty amazing. And that's what all those little spots that you see there are. Those are just different, they're volcanoes. And if you get to the backside, you can see that as well. So pretty neat. Pretty neat, really. Io is about the same size as our moon, but it's a lot more colorful. It makes me feel like we got ripped off on our moon, to be honest with you. But isn't that amazing? And what a privilege that's exactly what it looks like because we've had spacecraft that have gone past and mapped the surface. So that's what it looks like. So about the same size as Earth Moon, but far more colorful and far more volcanically active. And then we've got Europa's the next moon out. It's just slightly smaller than Earth's moon. And there's Europa. Pretty neat. And one of the interesting characteristics about Europa is it has these large streaks, especially on one side of the moon. Looks like a big cosmic cat came and just swiped it, right? We think those are probably geysers where water is spewing out from underneath. And that indicates that Europa has internal heat, and that indicates it can't be billions of years old. So Jupiter has internal heat, Io has internal heat, and Europa probably does too. And that indicates they can't be billions of years old because they would have cooled off by now. They would have cooled off by now. So, and by the way, Jupiter also has a very powerful magnetic field. And magnetic fields indicate it can't be billions of years old because the magnetic field would have run out by now, just like a battery runs down. The bigger the planet, the longer the magnetic field can last. Jupiter's a big planet, but after 4.5 billion years, it should be magnetically dead, and it isn't. So Jupiter's magnetic field and its internal heat both demonstrate it can't be billions of years old. It's consistent with the biblical time scale. This is Ganymede. Ganymede is the largest moon in the solar system. It's about 50% larger than our moon. And you can see it has all these interesting features on it, little craters. It's kind of tritone. It's got three colors: a bright white color, a darker brown, and then a really dark brown. So it's very pretty, I think. Very pretty little moon. And it's actually bigger than the planet Mercury. But because it orbits Jupiter rather than the sun directly, it's classified as a moon rather than a planet. But if you could separate it from Jupiter, it would be a planet, and that would be cool. So there's Ganymede. So of the four big moons, you got Io, Europa, Ganymede, and the outermost is called Callisto. So here's Callisto. It's just almost as big as Ganymede, but not quite. And it's pockmarked with all kinds of little craters all over the surface because, again, moons tend to not have a thick atmosphere. There's only one moon that has a thick atmosphere, and it's not these guys. So anything that comes nearby just hits it, and that creates an impact crater. So there's Callisto. Pretty neat. So those are the four big moons that were discovered in the year 1610. That was the first time we discovered moons beyond the Earth. Now, the inner moons of Jupiter, they all orbit in the same plane and in the same direction. So you can see some of those there. You can see the four big ones, Io, Europa, Ganymede, Callisto, and then there's four small moons that orbit even closer to Jupiter. And you can see if I speed up time, they all orbit in the same direction, and they all orbit in the same plane. That's a design feature because there's not a lot of space available there. And so if they orbit in different directions, they might collide, or they might get so close to each other that their gravity causes one of them to get kicked out. So that's a design feature. You only have to do that for moons that orbit close, though. The moons that orbit farther away from Jupiter, they're a little crazier, see? And if I speed up time, you can see a lot of them orbit backwards. So the inner moons are all going, see that? The inner moons are all going that way, and a lot of the outer moons go backwards. And they're all small, and it may look very crowded because the lines are thick, but there's actually so much space available out there that there's no chance of collision. So they can keep doing that, and it's not a problem. And they're not even in the same plane either. If we go edge on, you can see that they're all in different orbits there. Now, each one is a perfectly good elliptical orbit. It's just that they all overlap. They're all different orientations. So that's pretty neat. We're going to find that's a common design feature of planets and moons in the solar system. So that's the Jupiter system. Really neat planet. The next one out, Saturn, tends to be everybody's favorite. Yeah, because it's pretty. It really is. So there's Saturn. Look at that. And the planet itself is a lot like Jupiter. It's a ball of gas held together by its own gravity, hydrogen and helium gas. It's got clouds. It's got belts and zones like Jupiter, but they're more subtle. They're not as obvious, but they're there. And then the key distinctive of Saturn is, of course, that amazing ring system. And the Lord was kind enough to tilt that planet so that we could see the rings. And that's pretty nice. Because if Saturn were not tilted, you'd not know that it had rings. When they're edge on, you can't see them. Now here you can see the shadow because it's tilted relative to the sun, but if it weren't, they wouldn't even leave a shadow. So you would not know that Saturn had rings. So I think it's wonderful that the Lord tilted that planet, perhaps for our enjoyment. And that's also an indication that it didn't form from a cloud like the secularists believe, because you'd really expect all the planets would be upright. They'd be all orbiting the same direction at about the same speed and upright and not tilted like that due to a principle called conservation of angular momentum. So there's Saturn. Saturn has a powerful magnetic field like Jupiter. And whenever you have a magnetic field, that means it can't be billions of years old because magnetic fields decay with time. And so they can't last for billions of years. Saturn has a number of moons, quite a lot actually. It currently holds the record at 82. Saturn has 82 moons, as far as we know. There's probably more. And let's see, let's just look at a few of them here. There's Mimas. I really like Mimas. It orbits really close to Saturn. And there's a giant crater on one side. If we rotate it around, you'll see it. There's that massive crater. Can you see that right in the center there? Just huge. And when the sunlight hits it just right, it really looks massive. In fact, it looks kind of like the Death Star from the Star Wars movies. So, yeah, it's pretty neat. So I like Mimas. Well, let's do a couple others. Let's do, I don't know. We don't want to do all 82, but Rhea. You can see Rhea in a small telescope. It's one of the brighter moons. It's probably the second brightest moon of Saturn. So there's Rhea. Isn't that pretty? But the one that's really interesting, it's called Titan. And you can see this in a small telescope. Even in binoculars, you can see Titan. It's the second largest moon, which is kind of fitting because it orbits Saturn, which is the second largest planet. So it makes that easy to remember. And the cool thing about Titan is, of course, it's orange. It's an orange moon. And that's because it has a thick atmosphere. So you're seeing basically clouds that permanently enshroud. It's kind of like smog, really, that encompasses Titan. For a while, they thought it was the largest moon, hence the name Titan, right? But it's actually the second largest. The atmosphere makes it look bigger than it really is. It's kind of like a cat when they get upset and they puff out a little bit. So there it is. We've sent some spacecraft one spacecraft went into orbit around Saturn, that's a Cassini spacecraft, and it used radar to penetrate the surface of Titan. So we know what the surface looks like, because remember, radar can go through clouds, and here's what the surface looks like. So it's pretty neat that we can do that these days. And in fact, we've actually sent a lander. There's actually a little probe that landed on Titan and took some pictures of the surface. It's pretty interesting. So that's what it looks like. One of the things that's interesting about Titan, because it has that thick atmosphere, that atmosphere has a lot of methane in it. Methane's a hydrocarbon, like gasoline's a hydrocarbon, okay? So methane, and the thing about methane is it's destroyed by ultraviolet light from the sun. Ultraviolet light destroys methane. And so if Titan were billions of years old, why does it still have methane? Because it would have had plenty of time for that to be completely destroyed. And so it was astonishing to find not only methane in the atmosphere, but there's actually lakes of liquid methane on the surface of Titan. So no oxygen though, so you couldn't breathe there. That would be a problem. But gasoline would be cheap, so there's that. Because that's kind of what it's made of. One moon that's really cool, it's called Iapetus, and it orbits out pretty far from Saturn. And Iapetus is neat because one side is very, very dark, and the other side is white as snow. Isn't that wonderful? We think there's a reason for that. There's another moon that orbits further out, and debris from that moon collects on the leading hemisphere of Iapetus. But I just think that's a beautiful moon. And of course, you could see Saturn in the background, and it doesn't quite orbit in the ring plane, so you'd be able to see the rings. So, isn't that wonderful? Iapetus. Yeah. So those are some of the moons of Saturn. It has a lot of them, but one really big one that's Titan. So there's the Saturn system. Okay, now, in the 1980s, a wonderful thing happened. Jupiter, Saturn, Uranus, and Neptune happened to line up in a giant arc. And that allowed human beings to send one spacecraft past all of them, because it would use the gravity of Jupiter to slingshot it onto Saturn, to slingshot it onto Uranus, to slingshot it onto Neptune. Pluto was not part of the arc, so we couldn't do that. But it was, and that doesn't happen very often. So I think it's actually a little gift from God that right at the time where technology developed that we could send stuff into space, the planets happened to line up so that we could send one spacecraft past all of them. Because otherwise we'd have to send 4 different spacecraft, and that would be prohibitively expensive. We couldn't have done it. So in 1986, the Voyager 2 spacecraft flew past the planet Uranus because they were lined up. So you can see Saturn, Uranus, and Neptune, how they're lined up like that. And this is what it saw. That's the planet Uranus. It's about 4 times the size of the Earth. It's a big blue ball of gas and ice, probably. Uranus is tilted on its side, which again is really shocking to the secularists, because if the solar system had sort of evolved, you'd expect all the planets would be upright, and only a few of them are. So there's Uranus. So it rolls around the sun, because its North Pole, or South Pole, depending on how you define it, is pointed at the sun. Uranus has a very strong magnetic field, and magnetic fields mean it can't be billions of years old, right? Because magnetic fields get weaker and weaker with time, and so you would not expect it to still have one if it were billions of years old. But it's okay for thousands of years. It's still got enough energy left to keep going. Uranus has a number of moons. It's got 5 relatively large ones. Miranda, Ariel, Umbriel, Titania, and Oberon. Here's Miranda. Yeah. Look at that. And it's weird. It's weird because it looks like it's been broken apart and reassembled. It's got that big reverse check mark on one hemisphere there, so that's kind of neat. So if you're wondering about the names, they're named after Shakespearean characters, and that's because the planet Uranus was discovered by an Englishman, so they decided to name the moons after the greatest English playwright, allegedly Shakespeare. So Uranus is the only planet that does that. So there's Ariel. Anyway, that gives you kind of a feel for this system. It has rings like Saturn, but they're real thin, so they're not easy to see. So that's Uranus. And then the next planet out would be Neptune. So Neptune, the Voyager 2 spacecraft flew past Neptune in 1989 and got some really good pictures of it. Neptune is a beautiful blue color. Isn't that nice? And it's got thin clouds. You can see some of those white things, those are clouds, but it's also got some storms on its surface. It's got a great dark spot. We thought only Jupiter did that, but then we found out, well, Neptune does that too. It develops these big hurricanes. And now this one, unlike the red spot, this one comes and goes. Sometimes it's not there. And sometimes there's a different one that develops in the northern hemisphere. So we know that because the Hubble spacecraft can do almost as good as Voyager 2 did. So isn't that delightful? Beautiful planet. It's very much like Uranus. It's about 4 Earths across. It's got a magnetic field, which was a surprise. By the way, my friend Russ Humphreys, he's a creation physicist. So he's a Christian, and he believes that God created, like the Bible says, in 6 days, a few thousand years ago. He actually predicted the magnetic fields of Uranus and Neptune based on their age of 6,000 years. And he was right. The secularists were way off. So if you want to get the right answer, start with the Bible. There's a number of moons around Neptune. It's got one that's fairly large called Triton. And Triton's the only large moon that orbits backwards. So again, the Lord likes to do things like that just to confuse the secularists. So there's Triton. And one of the neat discoveries about Triton, when we zoom in on it, it's got these black sort of features on there. You see those black streaks? Yeah. Those are geysers. So this material shoots up, and it's got soot in it. That's that black stuff. And Triton has a thin atmosphere, and the winds cause the soot to sort of be deposited in horizontal lines. So that's what you're seeing there. But anytime you have activity like that, like geysers or volcanoes, that indicates there's internal heat in this little moon. It's not a very big moon either. And so the fact that it still has heat, even though it's very far away from the sun, tells us that this planet this little moon can't be anywhere near billions of years old. So, and you can see the surface kind of changes there to these other, isn't that interesting? What a weird surface. So that's the Triton of the Neptune system. It's got a bunch of other moons too, but most of them are very small, so we won't do all those. So that's Neptune. Now, when I was a kid, Pluto was a planet, okay? And then it got demoted, so it's not a planet anymore, but it's still there, and it's still interesting, and so we're going to look at it too, because in 2015, the New Horizons spacecraft flew past Pluto, and we got some really nice images of the Pluto system. So let's take a look at some of these. So there's what Pluto looks like. Now, when New Horizons was a flyby mission, it just flew by Pluto, and when it's far away, it took these pictures. So that's why they're not quite as clear, because it was far away. And then when it got close to Pluto, it got much sharper images of this side, and you see it's really interesting. And this was surprising to the secular astronomers, those who reject the Bible, because they were expecting that they think Pluto's 4.5 billion years old. It's 40 times farther away from the sun than the Earth is. And so you'd expect that it would just be completely covered with craters, because it can't have any internal heat. It's small. Pluto is small. It's only 2/3 the size of Earth's moon. And so it can't keep internal heat very long. It certainly can't keep it for billions of years. And so it should have run out of energy. So there shouldn't be geology. There shouldn't be mountains and valleys. There should just be craters, because there's lots of stuff out there orbiting near Pluto that you would expect would collide with the surface. And there are a few craters, but not very many. In fact, there's a section here that has not a single crater in it. Look at that. There's not a single crater there. But there's this sort of weird, like a jigsaw puzzle kind of. You see that? Isn't that wild? And we think that's caused by internal heat. So that's, and there's mountains too. You see these, I mean, they look tiny because, I mean, this is 2/3 the size of the moon, but you see those features there. Those are mountains, about as big as the Rocky Mountains in Colorado, but they're made out of ice instead of rock. Pluto is so cold that ice is as hard as rock at that distance. So there you go. But that indicates that Pluto has internal heat, or at least had internal heat recently, which means it can't be anywhere near billions of years old. There's lots of evidence like that. You just tend not to hear about it in the standard media or at the movies and what have you. So that's Pluto, and that internal heat demonstrates its biblical age of a few thousand years. Pluto has 5 moons, but only one of them is big, and it's very big. It's half the size of Pluto. It's called Charon. There's Charon. Yeah. There's what it looks like. See that? And it's got some craters too, but it's got mountains and valleys. Isn't that interesting? And it's got a dark North Pole, which we've never seen before, so that's kind of neat. Look at that. So pretty fun. And of course they've named the different features on these things, and this is kind of neat. You might get a kick out of this. The named features. They've started naming them because they've named features on all kinds of worlds, but they've started naming them after sci-fi characters with Charon. So you got Vulcan Planum, Spock crater, Kirk crater. How about that? Uhura crater, Skywalker crater, Vader crater. This one's Mordor, so they got some Lord of the Rings stuff in there too. So I think that's kind of I don't know if that'll catch on, but I approve. So, pretty neat, isn't it? So we live in really an amazing solar system. So I'm so glad we got to take a look at Pluto, because I always wondered what it looked like, and now we know. Now we know, because we got spacecraft that have gone past it and measured it. So, and it's weird. It's so cool looking. It really shows you the Lord's creativity in making all these wonderful objects, ultimately for His glory, but perhaps for us to enjoy as well. And so that's kind of, those are the main objects in our solar system. There are smaller stuff like asteroids and comets, and we could explore those as well. But we now know that other stars have planets orbiting them. And we don't know much about those other planets now, because we can just barely see them. And in some cases, we can't see them at all. We can detect them by other methods. But it's really pretty amazing. I mean, this is just one solar system, and look at how interesting it is. There could be 100 billion other solar systems just in our galaxy. And you could imagine in the future somebody picking one of those and showing how it declares God's glory with each of the worlds, each of the planets and moons of that system. Pretty neat. But for all of these amazing worlds out there, the earth really is very special. Isaiah 45:18, God formed it to be inhabited. Of all the planets, this is the one that God spent 5 of the 6 creation days working on. You realize that all the other planets are made on one day, day 4. God spoke them into existence. One planet, Earth, He made on day 1, and He took 5 of the 6 days to form and fill the earth, making it right for life. And so it's very special. Of all the planets that God created, this is the one he walked on. I think that's pretty neat. One of the astronauts, actually there were two astronauts who walked on the moon who later became Christians. And one of them said, the amazing thing is not that man has walked on the moon. The amazing thing is that God has walked on the earth. And I think it's pretty awesome. Because the God who spoke all those worlds into existence cares enough about you that he was willing to die to pay for your sins so that you could enjoy eternal life with him. That's pretty awesome. That's pretty awesome. So in the one sense, looking at all these amazing planets that are so big might make you feel very small, but the fact that the God who made all of them died for you ought to make you feel pretty special. That's pretty neat. So I think I will close there for this first session. So thank you very much. God bless.
All right, if we could spread the word, get everyone back in here, we're going to start. I think the high school kids are in the cafe. If somebody wants to go get them. CBI, come back and sit down. And I think elementary's left, so if you want to move closer, you can. All right, we're ready to begin. So if the high school students would come in and sit down, and CBI will be beginning shortly. You can move forward if you want. All right, I think we're moving the secondary school up. All right, again, let's welcome Dr. Jason Lisle.
Okay, so in this presentation, we're going to take a look at how science in general confirms biblical creation. When we look at the evidence, ultimately we look at it from the perspective that the Bible's true or that it isn't. And we all have one of those two biases, ultimately. People like to think they're neutral. Oh, I haven't assumed the Bible's true or assumed that it's false. Well, that's not really possible. We all come to the evidence with beliefs about how it should be interpreted. When secularists look at the earth, they tend to think in terms of billions of years of death, disease, suffering, and so on, producing the life on earth. That's about how evolution's supposed to progress, right? Certain kinds killing off other kinds and so on. Biblically, I'm thinking in terms of the 7 C's of creation. If you were here last night, we talked about those. But that's basically the biblical timeline. And where God created the perfect world, He created the initial animals and so on. They've diversified a bit since then. And so that's the history that I'm looking at. And all I want to do really is kind of whet your appetite here a little bit by showing you that the science confirms biblical creation. This isn't intended to be a proof of biblical creation. I have another talk and a book on that. But I do want to show you that the science is consistent with the Bible in 3 areas. So we're just going to kind of do an overview in the area, first of all, of genetics, which is the study of how traits are transmitted from one organism to the next. Information theory, which you may or may not have heard of, but it's very strongly confirmative of biblical creation. And then geology, rocks and fossils and things like that. So we'll start with genetics, and in fact, I'll spend the most time on genetics. And we'll see that genetics is the study of heredity, the study of how animals change. Do animals change? Do dogs change? Do they? Do they change? They do change. What do they change into? Dogs, yeah. Dogs change into dogs. And that's not evolution in a Darwinian sense, because they're never going to be anything other than dogs. But you can get different breeds. And that is something that God has built into the genome to be able to do that. And not just in dogs, but in other animals, and in human beings as well, and even in plants, which are not biblically considered living. But we would expect this. We would expect that animals do change, but they remain the same kind, because Genesis 10 times uses this phrase that God created animals and plants and whatever after its kind, or after their kind. Used 10 times in Genesis 1, we better take it seriously. By the way, kind does not mean species. Some people misrepresent what it is that creationists teach, or what the Bible teaches for that matter, and they'll say, well, creationists believe that God created all the animals as they are today. I don't believe that. I don't believe that there were poodles in the Garden of Eden, okay, because it was a paradise. You're not going to have poodles in it, right? So this is a misrepresentation of what we believe, okay? And some of them even say, well, yeah, creationists believe God created all the animals, even in their current locations. It's nonsense. Animals have migrated, and they've diversified into different, you can get to different breeds of dogs. Breeds of dogs are recent, like the golden retriever. It didn't exist 200 years ago. Dogs did, but that particular set of genes hadn't been isolated. And so what we actually believe in is variation within a kind. Animals do change. They do. And, so you've got all these different branches. Some kinds have gone extinct completely. Apparently, most of the dinosaurs, perhaps all of them, extinct. There are some ones where certain variations have gone extinct, but other variations of the same kind exist. Elephants, for example. We think mammoths are part of the elephant kind. They're genuinely related to elephants, and yet they're gone, but you still have African and Asian elephants. And so you can have that. That's fine. They remain the same kind. And we'll see why that is as we go along. In the evolutionary view, there really aren't kinds in the evolutionary view, because everything's related to everything else. All biologically descended from a common ancestor, which is something like a microbe billions of years ago. And so there's a complete continuum in the evolutionary view. You don't have these boundaries that would prevent one kind from becoming another. And I maintain that the top view, the biblical view, is consistent with science. The bottom view is not. Now, to see which of these is consistent with the science of genetics, we need to know a little bit about genetics. We need to know about DNA. That's a very long molecule that exists in the cells of your body. It looks something like a twisted ladder, and on the rungs of this ladder are nucleotide base pairs. There's 4 different varieties, and they're always abbreviated C, G, A, and T. And if one strand has a C, the other will have a G. C's and G's group, T's and A's group. But if you just look at one strand, C, G, A, T, you don't know which letter's going to come next, okay? So, and the arrangement of those letters spells out the instructions to make you. Pretty amazing. In the same way that I could spell help with beads on a rope in Morse code, I could spell, anything in DNA. It's got the instructions on how to make proteins that make up you, which is remarkable. And the reason that you are a person and not a cabbage is because you've got the instructions to make a person. And the cabbage has the instructions to make a cabbage. And you got the long end of the stick on that one. And by the way, some of those instructions are the same because you use some of the same proteins as a cabbage. That's really important, because if it weren't the way, God could have created all organisms with totally unique chemistry. But then the only thing we would be able to eat is each other. So that would be a problem, right? It's important that all organisms share some proteins, and therefore we'd expect them to have some similar DNA, because DNA is what makes the proteins. Now, you have 2 sets of DNA. You get one set from dad, you get one set from mom. They had 2 sets of DNA, and so on, all the way back to Adam and Eve, who had 2 sets of DNA. And when mom and dad have kids, you don't know which of the 2 you're going to get, but each child will get only one of the 2 genes. A gene is a section of DNA that controls a trait. You only get one of the 2 from dad and the other of the 2 from mom, and you don't know in advance which one it's going to be. It might be that one from dad and that one from mom for that particular gene, and then the next one you don't know. And so there's the child. Now the next child will get a different combination, right? The next child will get a different combination. Next child will get a different combination. There you go. So you might notice that you look a little bit like your dad, you look a little bit like your mom, and you also have some traits that neither parent has because you have a unique combination. Unless you have an identical twin, you have a unique combination. So you have some similarities with your siblings, if you have siblings, and you have some differences because you have a unique combination of DNA. Here it is with blood type. So with blood type, there's 3 alleles of possible gene. You have A, B, or O. And if you get A from dad and A from mom, your blood type's A. That's easy. If you get A from dad and O from mom, your blood type's still A because A is dominant, O is recessive. Maybe you remember studying that. And likewise, if you get O from dad and A from mom, your blood type's A. So sometimes one allele is dominant over the other. If you get B, BB, or B and an O, your blood type's B because B dominates over the O. If you get an A from one parent and a B from the other, your blood type's AB because they're codominant. The only way you can have blood type O is to have both O alleles. So you get O from dad, you get O from mom, your blood type's O. So those are the 4 blood types that occur in human beings. Okay? There's other complications, but that's the basic idea. Now, the thing that I find interesting is if mom and dad have this combination, let's say mom has blood type A, and we'll say it's the heterozygous A with an O and an A, and dad has blood type B, heterozygous B with the O and the B. The children could have any blood type. Okay, so the first child gets the A allele from mom, the O allele from dad, and that child's blood type is A, like mom. The next child gets the B from dad, the O from mom, the blood type is B, like dad. The next child gets the A from mom, the B from dad, and his blood type AB. The next child gets the O from mom, the O from dad, and has blood type O, which neither parent has. He says, am I adopted? No, you're not adopted, right? That's just, you have a unique combination of traits. So you might notice you have some traits that look like your mom, some traits that look like your dad, and some traits that neither of your parents have because you have a unique combination. Again, unless you have an identical twin. So that's how it works with blood type. Here's how it works with skin shade. So basically there's one skin shade, it's brown. Well, there's a couple different forms of it. There's a pigment called melanin that causes your skin to be dark. And it's just a question of how much melanin you have and how it's distributed in the cells. There's a couple different forms of melanin. There's a gray form and more of a yellow form, but this is just for the gray form. And so if you have the big A, big B, you're very, very dark skin. If you have lowercase a, lowercase b, you're very light complected. If you're in that bottom right box and you get married to somebody in that bottom right box, your kids are going to be in that bottom right box because only the lowercase letters are available. And so you get genetically locked in. That's what they call a homozygous combination. So there's very little variability there. And likewise, if you're anywhere on that diagonal that's highlighted there, and you get married to somebody in the same box, your kids will have to be in that box. But if you're off axis, if you're say in the upper right, where you have big A, big B, little b, you have a middle brown skin color, and you get married to somebody in that box, your kids could have any shade from very light to very dark, because all 4, you have all combinations possible there. And so we think Adam and Eve probably had a middle brown skin color. They wouldn't be white like is depicted in some children's books, right? They would have been a kind of a middle brown color. And really there isn't such a thing as a white person or a black person. We're all brown. It's just a question of how much, right? There's only one race, the human race. And so this is how you account for the different shades of skin. This is simplified, but this is really how it works. We're going to look at dogs because dogs have a tremendous amount of variation built into their genome. They have lots of big A, big B, little b, big C, little c. And as dogs reproduce, we can see how these different genes are expressed in the offspring. And dogs reproduce faster than we do, so it's they're really good for these kinds of learning studies. Now, in the evolutionary view, bacteria eventually evolved, something like bacteria, eventually evolved into horses. Okay? So these single-celled organisms that arose from the chemistry randomly millions of years ago, eventually, as they reproduced versions that are a little different until eventually you get a horse. I don't believe that, but my secular colleagues do. Now, if that's true, if that became that, I mean, the bacteria has some instructions in it. It's got the instructions to make a bacterium, right? A horse has a lot more instructions. It's not just that it has more DNA, which it does, but it has more instructions in its DNA. It's got instructions that the bacteria lack. A horse has DNA instructions to make bones. Bacteria do not have DNA to make bones, and they can't make bones. A horse has DNA information to make eyeballs and ears and hooves and teeth. Bacteria do not have those DNA instructions, and so they can't make those traits. So it seems to me that if something like bacteria eventually became horses, at some point, new information had to be added to the DNA. Does that make sense? In order for evolution to work, the information content in your DNA has to increase because you have to somehow gain the information to make new structures that you're currently not capable of making. That's really important. That evolution, in order for it to get off the ground, evolution in the Darwinian sense of, single-celled organisms eventually becoming horses, would have to involve brand new information being added. Evolution is all about an increase in information in DNA. And that's really important because the kind of processes we observe in nature reduce the information in your DNA, or are perhaps neutral. They don't increase it. One example of this would be natural selection. A lot of people have the misconception that natural selection is the same as evolution. It's not. It's actually the opposite. Natural selection is a true principle. It was written about by the creationist Edward Blythe before Darwin. Darwin hijacked it and tried to link it to evolution. But natural selection, as we'll see, does not increase the information in the genome, and therefore it can't possibly turn microbes into horses. So here's an example of how this works. So you have two dogs, okay? And let's suppose that each dog has a gene for short fur and a gene for long fur, and suppose those genes have a combined effect, and so the dogs have medium length fur. Now this is simplified, but the basic genetic principles here are true. And so if those two dogs fall in love and have pups, some of the pups are going to get the short gene from mom and the short gene from dad, and they're going to have short fur. Some of the dogs are going to get the short gene from one parent, the long gene from the other, and have medium length fur just like their parents. Statistically, 50% of the offspring would have that combination, right? And then 1/4 of the dogs will get the long gene from mom and the long gene from dad, and they will have long fur. Now, this is a great example of variation within a kind, because we started with dogs that just had medium length fur, and we ended up with different varieties, some that had short fur, some that had medium length, and some that have long. But we have no new genetic information. All the genetic information was in the original two. You had instructions for long, short, and by combination medium. And then it's expressed in the offspring, long, short, medium fur. Now, let's suppose that the environment gets very cold. What's going to happen? The dogs that have the shorter and medium length fur, they don't do so well in that cold environment, right? And so sadly, they die. Very sad. Okay. I didn't say natural selection was nice. I said it was true. Okay. The dogs that best survive in a cold environment are those that have the longer, thicker fur genes, right? And so they're going to find other dogs that have survived because they also have longer, thicker fur genes, and they're going to have pups, and their pups are going to have long fur. Because that's the only combination that's possible now, isn't it? We started with dogs that had information for long, short, and by combination medium, and we ended up with dogs with just information for long. Have we increased information? No, we've reduced it, haven't we? We've reduced the information because the information for short fur is now gone from the genome of that animal. Does that make sense? Now, if we started the experiment over, and this time we have all three varieties, long, short, medium, and this time let's suppose the environment gets very hot. Now the dogs that have the longer, thicker fur, they don't do so well in a hot environment. They die of heat exhaustion, sadly. Okay? The dogs that have the shorter fur, they survive because they're well suited to that environment. They meet other dogs that have survived because they're well suited to that environment. And they reproduce. They're going to reproduce dogs with short fur. Okay? This is a great example of adaptation. This is one type of adaptation where the environment got hot and the dogs that tended to do well in that environment and survive and reproduce were well suited to that environment. They had the short fur. And so pretty soon you find the animals that survive are the ones that have that characteristic. You'll notice the dogs didn't, it's not like the environment changed and the dogs thought, it'd be really convenient to have short fur now, and then they, made themselves have short fur. No, it's they already had short fur or they didn't. And if they already had short fur, they survived and reproduced, and if they didn't, they died. Or in many cases, it's not that extreme. In some cases, maybe you'll have a few dogs that have the medium length fur that are able to survive because they can find shelter. But because they have to spend most of their time in shelter, they don't have as much time to go out and find a mate and reproduce. And so they don't reproduce in as great of numbers. So sometimes it just reduces the population. But you'll find that the population, the typical traits in the population tend to fit the environment. Because if they didn't, they wouldn't have survived to be able to pass on those traits. And so we find that dogs that end up in the colder climates, sure enough, they have the longer fur, or they wouldn't have survived there. Those that end up in the higher environments, sure enough, they have the shorter fur. There's no problem there. And so you have 2 dogs, and that's all you need on Noah's Ark, 2 dogs, and they get off Noah's Ark, and they reproduce, and they spread away from the mountains of Ararat, and they take certain traits with them. And if the traits are not conducive to survival in a particular environment, those dogs don't make it. They're not able to survive in that environment. But if they do have traits that are suitable to that environment, then they do survive and they pass them on. And so dogs fit their environment. And then there's certain traits like eye color that really don't have a strong effect on survival. It's just a question of which dogs happen to go north and which group happen to go south and so on. It's called genetic drift. So, sure enough, dogs fit their environment. This is how we account for the different breeds, the different species, in some cases, of wild dogs. They're all just part of the dog kind. It's just a question of how the traits ended up in terms of the different environments. This is how we account for the different varieties of dogs in the natural world. Now, evolutionists would say, but Dr. Lisle, it's not just natural selection, it's natural selection and mutations. That's what drives evolution, right? Now, a mutation is basically a copying mistake, a copying error, a typo in your DNA, okay? And that's not a good thing to have because your DNA is the instructions that make up you. You don't want to mess with those instructions, okay? Mutations don't give you superpowers, they make you sick. They give you things like cancer and so on. But in any case, there are some mutations that are non-lethal. So, for example, let's suppose you have dogs with information in their genome for 4 normal legs, which all dogs should have. That's not a variable trait. They should all have that. But then when they reproduce, the DNA is not copied exactly right, and so some instructions are lost. And so the legs don't form quite right. You end up with a dog with short, stubby little legs, okay? And if you think about it, a dog like that is not going to do so well in the wild, is he? With those short, stubby little legs, he can't catch anything. He's more likely to be caught by something else. And so you're going to find that in the natural world, mutations can be reduced a little bit, maybe not completely, but they're held at bay because they tend to produce traits that are destructive to the animal. There are mutations that cause a defect in your heart. Your heart doesn't form properly. You're not going to pass that on. You're dead. There are certain mutations that are lethal, and those are not passed on. There are some mutations that are just inconvenient, like ending up with short, stubby little legs, and so that dog maybe is not as likely to survive. You're going to find that in the wild, mutations are held at bay because the animal dies if it has too many. But some people like dogs with short, stubby little legs because they can't jump up on you as much, and so they will take dogs with short, stubby little legs and care for them. And so that dog doesn't have to survive in the wild. He has a human caretaker who spends millions of dollars trying to keep him alive, okay? And so you'll find people that like dogs with short, stubby little legs. They'll find other dogs with short, stubby little legs and breed them, and you'll end up with lots of dogs with short, stubby little legs. They don't have to survive in the wild because they have human caretakers. Domestic breeds of dogs are full of mutations. And that's why, because natural selection doesn't come into play as much because humans take care of these creatures and put them in an environment where they can survive. There are all kinds of mutations in domestic breeds. There's a mutation that causes a dog's snout not to form properly. A dog is supposed to have a long snout, and that helps with its ability to smell. There's a mutation that causes the snout to be short, but the skin was designed to fit the longer snout, so the skin hangs off the side if you don't clean it and get infected, and some people think that's cute. You think the dog says, gee, I love having my nose stuffed into my face. That's great. And by the way, the chin was designed to fit the longer snout, so the dog has a horrible underbite. Probably not so pleasant from the dog's point of view. But again, he has a human caretaker who can keep him alive. Poodles have all kinds of problems because they have mutations that have accumulated in their genome. And these are just some of the problems that they can have, either as a result of a mutation or a secondary result. For example, we talked about earlier genes that regulate fur growth. That gene has been damaged in poodles. Poodles cannot regulate their hair growth. Their hair grows forever. which means if you don't give them a haircut every now and then, you end up with a big poof ball, right? Now this animal could not survive in the wild. It couldn't. But trying to drag all that hair behind it, no way. That's why you don't see documentaries about the wild poodle stalking its prey, right? You're not going to see that. They need a human caretaker to give them a haircut every now and then. If you don't, the hair will get in their eyes, they can get infected and go blind, and get in their ears, they can get infected, it can kill them even. So this is how we account for the different breeds of domestic dog. It's the initial information that God put in there, plus mutations, mistakes that have crept in, that have caused some little problems, and that's why purebreds tend to have some problems, and you have to spend a lot of money to keep them going. So we think the original dogs that would have been on Noah's Ark would have been like the wolf kind, because wolves still have a lot of heterozygosity, big A, big B, little b. They can produce a lot of variation. But as you selectively inbreed the dogs, you get down to something like a poodle, and that's kind of it, right? But you haven't added any new information, and that's the point. Remember, evolution requires an increase in information in the DNA. If you're going to turn bacteria into horses, you got to increase the information in the DNA. Mutations and natural selection and artificial selection, they don't do it because you're just getting down to the poodle, but you haven't added any new instructions. You can think of the information in your DNA like jelly beans. You got the coyotes, lots of jelly beans because they're kind of wild. The dingoes, lots of information. Then you get down to the purebreds. You concentrate those mutations. You're reducing the information until you get down to the poodle, and then that's kind of it. Poodles have kind of the minimum information that is necessary to keep them alive, and that's it. Now, could you possibly turn a dog into a cat by removing jelly beans? No, because you see it's got Jolly Ranchers. It's got different information in it. You can't get different information by removing information, right? That's not going to work. So there's no way you could turn a dog into a cat by this kind of process. And so you see when we take a look at dogs and we see how they reproduce, we find, lo and behold, they reproduce dogs. Different varieties to be sure, but they're always dogs. And that's consistent. That's observational science. It's testable and repeatable in the present, and it's consistent with the premise that God created the dogs to reproduce according to their kinds. It's not consistent with the evolutionary idea that dogs have evolved from something that's not a dog, because they need brand new information in their genome, and mutations don't do it. I do have to point out that sometimes mutations can be beneficial in the sense that there are some circumstances, they're kind of unusual, but they can happen, where a mutation can result in a trait that actually helps the organism to survive. Might call that a good mutation, and there are several examples of this. I'm just going to give you one, antibiotic resistance. You've heard about bacteria becoming resistant to penicillin. That does happen, and I'll show you how it works. There's a bacterium called H. pylori, which causes stomach ulcers. And you can get rid of this little guy by taking an antibiotic. You go to your doctor, he gives you an antibiotic. The antibiotic, which is harmless to you, goes into the bacterium, it's absorbed in his system, and he's got an enzyme that's part of his system, a protein, that when it interacts with that antibiotic, it converts it into a poison, which kills the bacterium, but is harmless to you. Pretty neat. And you say, oh, I feel better. No more stomach ulcers. There is a mutated form of H. pylori that lacks the ability to produce that enzyme, or at least he can't produce very much of it. And so the antibiotic goes into him, and it just sits there because he's missing some instructions. He's missing the instructions to produce the enzyme that would convert the antibiotic into a poison. And so it doesn't kill him. He's a resistant strain. And so you'll find in hospitals, for example, you have lots of resistant strains because the ordinary bacteria have been killed off by the antibiotic. And then the resistant ones are the ones that are able to reproduce. Is this evolution in the Darwinian sense? No, because we haven't gained any new instructions. We haven't gained any information. He actually lost some information. It's just that in the environment where you have a nuclear dose of antibiotics, it actually helped him to survive. In the wild, these guys don't compete well with those ones because that enzyme does something that's helpful. It's just that in an environment where you've lots of antibiotics, it helps them to survive. So mutations don't add new information. They might help you survive. They do not add new information to the genome, and therefore they can't possibly drive evolution. Dr. Lee Spettner, one of the world's experts on this topic, he's a PhD in biophysics, Johns Hopkins University, says all point mutations that have been studied on a molecular level turn out to reduce the genetic information, not to increase it. He says not even one mutation has been observed that adds a little information to the genome. This is devastating to an evolutionary perspective, because in the evolutionary view, we're made of information increasing mutations. You got 3 billion base pairs in your DNA, times 2, one from each parent. And those are supposedly built up by new information that has accumulated over time. We never observe that in science. So when we take a look at DNA and mutations and we observe scientifically how they work, we find that it's consistent with God creating the original information in the genome of all organisms, including human beings. And then we've lost some over time. We haven't gained any new information. There are some situations where losing information helps you survive, but those are kind of unusual, and they certainly don't drive evolution. That's the point. All the information to make all the instructions to make all the proteins in you was in Adam and Eve. Pretty neat. And the number of unique combinations, by the way, the number of unique children that Adam and Eve could have had before they would have 2 that were likely to be identical, is greater than the number of atoms in the universe by an enormous amount. It's an ingenious system to generate copious diversity. Well, we've been talking about information. There's a whole branch of science that deals with information and how information is transmitted and its source and so on. So what is information? I mean, we kind of have a feel for it, right? I mean, a computer program would have information in it. A book has information in it. But how do we define it? There's a few different ways, but one way that's really convenient is the Werner Gitt definition, which involves the following. Information always entails 3 things. 1, a symbolic code system. So if I pick up a book and it's got the word horse in it, I don't actually see a horse there. It's not an actual horse that's in the book. It's a word that represents the animal. And if you think about it, that all language involves words, which are symbolic code systems that represent something else, right? So information always has a symbolic code system. It always has language. It always involves language. Language that, in the case of the books that I read, they would be English. Okay, I can read a little bit of Hebrew, but not much. But in any case, there's grammar and syntax, right? The words are organized into sentences, into paragraphs, and so on. There's grammar and syntax, so there's language. And then finally, there's meaning. I could learn something from reading this symbolic code system that is organized in language. I could learn something from it. There is an expected action that the reader will take. There's an intended purpose. Let's take, for example, a cookbook. A cookbook fills all these 3 criteria, right? Because it's got a symbolic code system. It says 3 tablespoons. Okay, that means I don't actually see 3 tablespoons. I see those words which represent 3 tablespoons. There's a language convention. Okay, it might be English. Take this, combine it with that, and so on. There's an expected action. The expected action is that the person reading the cookbook will combine the ingredients in the way that the book says. And there's an intended purpose. The purpose is so that you won't go hungry. Okay? So a cookbook fulfills all those 3 criteria. The Bible does too. The Bible's got a symbolic code system. It's got words that are organized into sentences. It's got a language, originally written in Hebrew and Greek, but you can read an English translation of it. That's fine. And there's meaning. There's an expected action that we will obey God, that we will repent and obey and believe the gospel. And there's a purpose that we might have eternal life. So the Bible fulfills that as well. And really any book you can think of would have all of those criteria. So you got it? Symbolic code system, language, meaning. So could this be information? Could be. Looks like there's probably a code system there. Looks like there are icons that represent something else. Looks a little bit like hieroglyphics maybe. It looks like there's language because the way they're organized, it looks like they're organized into sentences. Is there meaning? That's the tricky one. And the only way you can know if there's meaning is if you know the translation. And I happen to know the translation to this. This is Genesis 1 through 5 in the form of icons, right? In the beginning, you see like the movie clipboard, in the beginning, God created heaven and earth, and the earth was without form and void, and darkness was upon the face of the deep, and the Spirit of God was hovering over the waters. It's Genesis 1 in the form of icons. That's kind of neat. So there is information here. Code system, language, meaning. Now it turns out whenever you have information, there are certain laws of nature that apply. Just like when you have energy, there's the law of conservation of energy, which says you can't create or destroy energy, you can only transform it. Okay? So it's the same with information. And Dr. Werner Gitt, one of the world's experts on information theory, gives some of these laws or theorems. He says there is no known law of nature, no known process, and no known sequence of events which can cause information to originate by itself in matter. It appears to be a law of nature that information does not spontaneously generate in a natural system. What does that mean? Well, if you take a box of alphabets, right? The cereal that's all little letters, and you mix them up in a box. You open it up. Don't expect to find Shakespeare, right? Don't expect to find instructions on how to build a warp drive. Right? You're just going to find a random assemblage of letters. Information does not spontaneously generate in matter. Okay? Well, then where does it come from? If information doesn't just accumulate in matter, where does it come from? You know the answer to this. Dr. Werner Gitt says when its progress along the chain of transmission events is traced backwards, where did this information come from? Where did it come from? Where did it come from? Trace it backwards. Every piece of information leads to a mental source, the mind of the sender. Information always comes from, ultimately, a mind. And you knew that, right? You pick up a book, you wouldn't assume, well, the information in this book, this was probably produced by an explosion in a typewriter, right? You would say, well, there's useful information here. Well, where did the information in this book come from? Probably from a printing press that makes a lot of them simultaneously. Where did it get its information? Probably from a computer. Where did it get its information? From another computer. All the way back to a mind. Somebody wrote it. Somebody wrote it. That makes sense. Information always comes from, ultimately, a mind. Now, a non-mental process can copy information. A Xerox machine can copy information, but it can't create it. Right? Put a blank piece of paper in a Xerox machine and see what wonderful works of literature it will produce. It will produce nothing because it can only copy information. It can't create it. It can lose information. You put your thing in the Xerox machine, it's run out of ink, and you're like, oh, that's a problem. But it can't create new information. Why is this important? Because what does DNA have in it? Information. All the instructions to make you. Interesting. Where did you get the information in your DNA? We covered that earlier. You got it from your mom and your dad. You got half of your information from each parent. Where did they get their information? From their mom and their dads. And so on, all the way back to Adam and Eve, who got it from the mind of God. Oh, so information does come from a mind. Creation is consistent with the laws of information theory. Evolution is not. Evolution violates the laws of information theory because evolution says the information in our DNA came about by chance in nature. But that violates every law that we know of in terms of information theory. Information always comes from a mind and never from anything else. And by the way, evolutionists know in their heart of hearts that information only comes from a mind. I know this because I did a little social experiment a few years ago. I posted this article called On the Origin of Articles. And the article is supposed to convince you that articles do not have authors. They're not written by anybody. Rather, articles are just sort of a property of nature. They probably started out as a single letter that was copied, and occasionally mistakes are made that added more letters, and eventually they accumulated into words, which accumulated into sentences and paragraphs. And as articles are copied over millions of years, the mistakes creep in and make the article better and longer. Granted, most mistakes make the article worse, but those ones don't get copied, right? It's kind of a natural selection thing. So basically, the conclusion of the article is that you're pretty much an idiot if you think articles have authors. They're just a property of nature. They happen by chance. Now, the funny thing was not so much the article, which is an obvious satire, but the response that I got to it. Because I had evolutionists chime in and say, we know you wrote this, Dr. Lisle. I said, how do you know that I wrote it? Did you see me write it? No? Oh, you're just taking it on faith? That's interesting. Oh, well, we could trace it back to your IP address. Well, that would just demonstrate that I posted it, which I freely admit. When this evolved on my computer, it was too good not to share it, right? It's interesting. I got to play the part of an evolutionist and defend the evolutionary view of articles, pointing out, and it's just funny, the arguments they would try to use. And I kept defending the evolutionary view just to mess with them, just to kind of get them to think through the issues. Yeah, well, we know, oh, come on, we know articles have authors. How do you know that? At best, you can only know that for an article you wrote, but obviously these articles came about by chance over millions of years. I mean, if you want to believe articles have authors because you're one of those authorists, I mean, that's fine, but keep it in church, man. Right? And now they could easily have refuted me. They could have easily said, we know that you or someone wrote this article because it has information in it. And information always comes from a mind. Not one of them used that argument. You know why? Because then they'd have to give up evolution. They would rather be absurd than give up evolution. Well, the Bible says as much. The fool says in his heart, there's no God. Anyway, what about geology? We need to talk about rocks now and fossils, that kind of stuff. And the first myth that I need to blow up is the idea that we know these rocks are billions of years old because of radiometric dating. That's what you'll be taught if you end up going to a secular university at some point, or frankly, if you read a secular textbook or watch the media or anything. Radiometric dating. So how does that work? Well, let me show you how it works and how it really doesn't. So we're all made up of atoms, right? These little particles that have protons and neutrons in the nucleus and electrons swirling around. Most atoms are stable, which means they will remain the same type of atom forever. Like carbon-12 will remain carbon-12 forever. And most atoms are like that. But there are some atoms that are unstable or radioactive. And what that means is they would really rather be a different type of atom. Like uranium, this is supposed to be uranium-238. It will spontaneously change into thorium-234. You don't have to do anything to it. It'll sit there and be uranium for a while, and then pop, it'll give off 2 protons and 2 neutrons and turn into thorium-234. Thorium-234 is also unstable or radioactive. And so it'll sit there for a while, and then suddenly it'll turn into the next element, which turns into the next one, and so on. And it emits energy when it does this, okay? All the way down to lead-206. Lead-206 is stable. Once it reaches lead-206, it'll remain lead-206 forever, okay? And so the bottom line is, if I had a chunk of solid uranium, and I waited for a long time, it would have some uranium and some lead in it, and eventually it would only be lead. Uranium spontaneously changes into lead. And the rate at which this happens is very slow. Actually, for a given atom, you don't know when it's going to change. It seems to be random, but if you have a large collection of atoms, statistically you know that it would take this much time for it to change into lead. It's kind of like popcorn. You don't know when the next kernel's going to pop. But you do know that after 2.5 minutes, you're done, right? So the idea is I have a rock that has some uranium and some lead in it, okay? And I can, that I've dug up from the earth, and I can figure out when it was all uranium because I know the rate at which uranium changes into lead. Does that make sense? But how do I know it's all uranium to begin with? And by the way, evolutionists do not assume that it was 100% uranium to begin with. It might have had some lead in it to begin with. Well, how much lead should we start with? Well, you tell me how old you want the rock to be, I'll tell you how much lead it started with. Right? Okay. So that's one of the assumptions of radiometric dating. There are 3 primary assumptions that are involved because you need to understand, folks, you can't measure the age of something scientifically. People have misconceptions. They think you pick up a rock, you scan it with your tricorder, it measures the age of coals, and it tells you the age of the rock. That's not how it works. What you're measuring are ratios of uranium to lead, and then you're trying to make a guess about what the initial ratio of uranium to lead was. And assuming that the rate's constant, you arrive at an age estimate. Let's suppose I had an hourglass in here. When you all came into the room and there was an hourglass that looked like that. And I say, how long ago did I turn that over? You'd say, well, it's an hourglass, so I'd say about a half an hour. I'd say, wrong, I got you. I actually turned it over only 1 minute ago, but already a lot of the sand was in the bottom chamber. You see? You can't assume that all the sand was in the top chamber. You can't assume that the rock was all uranium to begin with. Sand going from the top chamber to the bottom is like uranium turning into lead. How do you know what it started with? And secularists, they're not stupid. They've got some ideas about how to make a guess about the initial uranium to lead, but it is a guess about the initial uranium to lead. How do you know that I didn't add sand when you weren't looking? Uranium is leachable in salt water. It can move in and out of the rock. It's not a closed system. How do you know the throat of the bottle's always been the same size? How do we know that the sand has always flown from the top to the bottom at the same rate that it does today? Now, with an hourglass, that's probably a pretty safe assumption. But we don't know exactly why radioactive decay happens at the rate that it does. And therefore, it might have been different in the past. And we think there's very good evidence that, in fact, radioactive decay happened much faster in the past. We know you can change it. I was taught in school, I went through a public school system, I was taught that nothing can change the rate of radioactive decay. We now know that is false. Scientists have been able to speed up certain kinds of radioactive decay in a laboratory by a factor of 1 billion. The rhenium-osmium reaction, we can make it go 1 billion times quicker. All you have to do is strip away the electrons from the atom, and it'll decay much quicker. So there could be processes in nature that do that. So here's the thing. These are some of the assumptions of radiometric dating, that you know the initial ratio of uranium to lead or potassium, argon, etc., that the decay rate is constant. There's compelling evidence it's not. The rate research team did some wonderful research where they all but demonstrated that radioactive decay was faster in the past. And third, the system is closed, that no materials moved in or out. But we know that one or more of these is false because we've tested radiometric dating on rocks of known age. When Mount St. Helens erupted in 1980 and there was some subsequent eruption, it produced brand new rocks from the magma. And when the rock hardens, that's supposed to set the 0 point of the clock, because when it's magma, minerals can move in and out. So we took brand new rocks, we sent them in and had them radiometrically dated. We sent them to a secular lab so we couldn't be accused of bias. And they came back, these brand new rocks, less than a year old, came back with estimated ages of hundreds of thousands to millions of years. That's a fact. Radiometric dating has been shown to not work on rocks of known age. It's assumed to work on rocks of unknown age. That's the bottom line. Be kind of like if I gave you a calculator. Merry Christmas, here you go. 2 plus 2 equals 57,423.1. I say, don't worry, it works on big numbers. Would you be satisfied with that? Would you say, oh yeah, this is a good gift? No, you'd say, I think I want to trade this in for something else, something that works. That's radiometric dating. It has been shown to not work on rocks of known age. Now, occasionally it'll give the right answer. Occasionally it'll give a negative answer. Did you know that? You can hold in your hand a rock that, according to radiometric dating, has not formed yet and will not form for another 1,000,000 years. It's true. The isochron methods sometimes give negative ages. Anyway, what about carbon dating? Some people have the impression that carbon dating gives the millions of years. It never does. It never does. Carbon dating, now it's based on assumptions too, but we think with carbon dating they're a little more reliable. Because for one thing, when we carbon date stuff of known age, it tends to give the right answer. Or within the ballpark of the right answer, within a factor of 10. So it's not going to give millions of years. The way carbon dating works is most carbon is C12, got 6 protons, 6 neutrons. There's a variety of carbon called C14 that has 2 extra neutrons, which makes it unstable. Okay? So and C14 is produced in the upper atmosphere when cosmic rays bombard nitrogen atoms. That converts them to C14, and they would like to convert back to nitrogen, and they will do so with a half-life of 5,700 years. C14 does not last millions of years. It lasts 5,700 years is the half-life. So the idea is when you're alive, you are eating plants. Plants get some, there's carbon dioxide in the atmosphere, and 1 atom in a trillion of those carbons is C14. So the plants take that in, they use the carbon to build themselves, and then they release the oxygen. So plants have a little bit of C14 in them. You eat the plants, or animals eat the plants and you eat the animals. Either way, you get new C14 in you. So a small fraction of the atoms in your body are unstable. You're all slightly unstable, right? Now, the C14 in your body is constantly decaying back to nitrogen, but you replenish it because you continue to eat, right? Most of us do it every day. And so you replace it with new C14. And so the C14 to C12 in you is about the same as it is in the environment until you die. And then when you die, the C14 simply decays away. So while you're alive, it stays constant, and then the moment of death, it starts to decay away. And if something were 1,000,000 years old, it would have 0 C14 in it. Because remember, the half-life is only 5,700 years. Carbon-14 does not last that long. And yet we find it in all kinds of fossils. Dinosaur fossils, they have C14 in them, which means they can't be millions of years old. Diamonds that secular scientists think are 1 to 2 billion years old, they have C14 in them. Can't be billions of years old. There are hundreds of processes like that set the age of the world as much less than the millions, let alone billions of years. And so the rate at which salt flows into the ocean, this is one of the first ones I learned, and it's good, it's compelling. So even fresh water has a little bit of salt in it because it picks it up from the land, and then it dumps, and the rivers flow into the ocean. Now the water from the ocean evaporates, but that leaves the salt. And so then it rains, and so every year the oceans get just a little bit saltier. Every year 450 million tons of salt from all the rivers in the world is dumped into the ocean. Evaporation recycles the water, but not the salt. You can get rid of a little bit of the salt with salt sprays and things like that, but most of it just accumulates. The oceans have been getting saltier since creation, okay? And so how long does it take for that process to happen? Well, even being very generous to the critics, 62 million years is all it would take to get the Earth's current amount of salt in the ocean, assuming it started as fresh water, which we don't believe it did. We think it started as salt water. So the actual age would be much less than 62 million years. But the point is, 62 million years is the maximum possible age of the ocean based on the salt content. And yet, secularists believe the ocean is 3 billion years old. That's a problem, because the maximum possible age based on salt content is 62 million years. And again, that's not the true age, that's a maximum possible age. So it's consistent with the biblical age of 6,000 years, because we think the ocean started already salty, and it's got just a little bit saltier since creation. But it's not consistent with 3 billion years, right? Because 3 billion is greater than 62 million, right? For those of you that are Common Core educated, I just want to make sure. Okay. The rate at which mud accumulates on the ocean floor, 20 billion tons per year. Because rivers wash out not only salt, but they wash out mud onto the ocean floor. It accumulates. How long does it take to get the current amount of mud on the ocean floor? Assuming it started with none, assuming there was no worldwide flood, which there was, 12 million years maximum. You get all the mud that's there. Of course, the worldwide flood would dump a lot of mud quickly, so that's why there's even that much. The true age is much less than that, but that's a maximum possible age. But yet the secularists believe the ocean's 3 billion years old. Can't be older than 12 million years based on mud accumulation. There's a lot of stuff like that gives a maximum possible age that is much less than the secular age, but is perfectly consistent with the biblical age. Human population. How long does it take to get Earth's current population? It doesn't take millions of years, that's for sure. We've been able to measure the population, or at least estimate it, throughout history. And it's consistent with about 4,500 years. Why not 6,000? Because humanity had to start over when there was the Great Flood, because it was just Noah and his family that survived that. But the best evidence that the world's thousands of years old is we do have the birth certificate of the universe. The Bible tells us God created in 6 days, humans were made on day 6, and it gives us the genealogies so you can find the approximate time between Adam and Christ's earthly ministry. The bottom line is the secular scientists say the Earth's billions of years old, take my word for it. God says I created in 6 days, take my word for it. And God was actually there, so anyway. Well, what about these fossils that we find? I was always sort of given the impression that an animal dies and then over millions of years it's covered with sediment and then it slowly fossilizes. Fossils speak of catastrophic activity generally. This is a fossil ichthyosaur. It's a marine reptile that evolutionists believe lived millions of years ago, but in any case. This was killed, buried, and fossilized in the process of giving birth. Do you see the baby ichthyosaur being born there? They're born tail first because they're an air-breathing reptile that's underwater. And so as soon as they're born, they have to swim to the surface to get their first breath of air, which is kind of neat. I wonder how the evolution turned that thing around, because most organisms are born the other way. But no, that's a design feature. There's a fish fossilized in the process of eating another fish. Catastrophe, not slow, gradual millions of years. By the way, most things don't become a fossil at all. Right? You come across a dead animal on the side of the road, it doesn't slowly fossilize over millions of years. So let's say you have your dead cat, Earl, okay? And You want to, he's been generous enough to donate his body to science, so we're going to watch him slowly fossilize over millions of years. Okay, let's wait a little while. Day 1, dead cat on the grass. No surprise there. Day 3, smelly dead cat on the grass. Yeah, he's starting to decay. Day 9, very smelly dead cat on the grass. Day 20, parts of Earl are missing. Day 38, more of Earl's missing, and eventually Earl is missing. And that happens. When an animal is killed and it's on the side of the road, it doesn't slowly fossilize over millions of years. It doesn't turn into a statue. It is recycled into the environment, for which we should be grateful. Scavengers will come and pick off the soft parts. Eventually, even the bones decay back into the environment. No, if you want to fossilize something, you have to bury it to protect it from environmental exposures. So, and even then, I was given the wrong impression. I was told the fish dies, it sinks down to the bottom, and then over millions of years, because these sediment layers are supposed to be millions of years to accumulate. Well, if that were the case, then if that layer happened a million years after that one, the top part of the fish would have had plenty of time to decay. You have to bury the whole thing fairly rapidly for it to fossilize, and most fish float anyway when they die, so that's not going to happen. We find fossil fish all over the world, by the way, even on mountaintops. Interesting. If you really want to form a fossil fish, here's how you do it. You go home to your aquarium, and you got your fish there, blissfully unaware of what's about to happen to him, and you dump some concrete on him. Okay. Now, this is probably illegal in California, actually. But anyway, so that's going to kill him. It's going to also simultaneously bury him, isn't it? And usually there's enough bacteria left in there, they can eat away the soft parts of the fish until the bone's left. But then the minerals in the water will move in and fill in the holes in the bone and make a stone in the shape of a bone. And that's what a fossil is. It's a mineralized bone. That's how you form a fossil. Does it take millions of years? No. We can fossilize things in a laboratory in a matter of weeks. It doesn't take millions of years. I could show you a number of examples of that, but I want to move on here. So what about the kinds of organisms that we find? Do we find examples of evolution? Is this the evolution of the horse? Well, I see different varieties of horse there, but they're horses, right? And they can, you can line them up because some are bigger than others. There's slight differences in the feet because modern horses have the single toe, but there are some varieties that had 3 toes in the past. But they're still horses. There's variation within a kind. And you say, but they're different sizes. Well, there are different sizes of horse today. These are both adult horses. They're just different breeds. There's lots of variation within a horse kind, and some variations that have gone extinct, like the ones that had 3 toes rather than 1. But what we don't find is a non-horse changing into a horse. So the only place you'll find one kind changing into another is in the pictures of the textbooks, but you won't find actual fossils of that. What about the rocks in which these fossils are found? Don't rocks take millions of years to form as mud slowly turns into rock? Here's a set of car keys embedded inside solid rock. I'll leave it to you to think whether that happened millions of years ago. Here's a man-made clock embedded inside solid rock. That's the one rock we know exactly when it happened, right? It's got a built-in clock. That's kind of neat. What about these layers? Look at all those layers of sediment, some of which are lithified. They've turned into rock. There's a person down there at the bottom for scale. Surely those took millions of years to form, right? Actually, none of those existed before 1980. Those are sedimentary rock layers that were laid down by the pyroclastic flow from the Mount St. Helens eruption. One volcano did that, and a fairly minor volcano. Mount St. Helens is pretty piddly by volcano standards. It laid down all those rock layers and I think the top layer is a subsequent eruption. And then it cut through those layers too, because it sloshed a wave in Spirit Lake that went through and cut out a canyon 1/40th the scale of the Grand Canyon in a matter of hours. One volcano. One. That's what it did. Laid down those rock layers, made a canyon 1/40th the scale of the Grand Canyon in a matter of hours. It doesn't take millions of years to form rock layers or to form canyons. It just takes catastrophic conditions. Think about the worldwide flood. The Bible says all the fountains of the great deep burst forth. That might refer to underwater volcanoes, we're not sure, but imagine all the volcanoes on Earth going off. If one volcano can do that, imagine what all of them can do. They used to tell you that these layers right here, these horizontal layers, laminations, like you'll find in the Grand Canyon, that they're annual. year. Each one was formed the year after the next. And you add it up, there's millions of them. Therefore, millions of years. See, you creationists are crazy. The evidence indicates millions of years. Except these are not from the Grand Canyon. These are layers that were laid down in the Mount St. Helens eruption. None of these existed before 1980. It turns out the way the mud flows produces those laminations. They were all formed at the same time. They're not annual. And those are the same type of features you find in the Tepete sandstone, which extends throughout most of the United States and Canada. It's a continental catastrophe that did this, at least continental. A global flood would do that. We find trees buried vertically in rock layers. That's interesting, without roots. Trees without roots buried in rock. Don't most trees have roots? I mean, that's kind of odd, isn't it? A little bit of coal down there at the base. I was always taught that coal forms from peat in swamps, that over millions of years the peat becomes coal. But the funny thing is we find, occasionally in coal you'll find impressions of leaves of plants, and that tells you what kind of plants were there. And they're not the kind of plants that grow in swamps. They're the kind of plants that grow in mountain rainforests. So think about that. What would uproot a tree in a mountain rainforest and deposit it quickly and compress the material? Worldwide flood would do that. See, we know how this happens now. Why is it that we find trees buried vertically without roots? Mount St. Helens did it. Because what it did is there was the explosion uprooted trees like matchsticks. You can see videos of this. It's amazing to watch. And then it blasted them in. So that's why they don't have roots. They were derooted when the volcano exploded. And then they tended to get pushed into Spirit Lake, nearby lake, where they tended to float vertically because of the little remnants of the root that were heavier than the rest of the tree. Occasionally they'll be horizontal, but most of them are vertical until they get waterlogged, and then they sink down, and the sediment from that explosion then covers them up. We know how this happens. And it's not millions of years. It's catastrophic conditions. So you see, when we take a look at rock layers and the fossils within them, we apply good observational science, we see what happens today, we find it's consistent with creation and a global flood. It's not consistent with the millions of years view. So when you see these massive rock layers, and especially sedimentary rock layers, those that are deposited by water, you shouldn't be thinking, well, that took millions of years. You should be thinking, that's the judgment of God. That proves that God is righteous because he will judge sin. And so the real message of the rocks is repent. That's really what they mean. You need to repent and believe the gospel. The Bible predicted that people in the last days would deny a worldwide flood. 2 Peter 3, beginning in verse 3, knowing this first, that scoffers will come in the last days, walking according to their own lusts, and saying, where's the promise of his coming? For since the fathers fell asleep, all things continue as they were from the beginning of creation. That's the doctrine of uniformitarianism, the belief that things have always been like they are now. No worldwide flood, come on. Verse 5, for this they willfully forget, or they're deliberately ignorant, that by the word of God the heavens were of old, and the earth standing out of water and in the water, by which the world that then existed perished, being flooded with water. It says they willfully forget that worldwide flood. So the Bible can be trusted, it's true. And it's because Adam sinned that we need a Savior. And so just as we see all this evidence for the worldwide flood, we're reminded that God is also a God of mercy and grace. Noah found grace in the eyes of the Lord. He was spared because of his faith in God. And so God instructed him on how to build the ark that allowed him physical salvation. I think it's interesting too, the Bible says that God was the one that closed the door on the ark. God was the one that decided time of mercy is over, time of judgment now. And we don't know when that's going to be for each of us. It's appointed once for men to die, and then comes judgment. But today's the day of salvation. So again, check out the resources. We got Ultimate Proof of Creation, giving you a bulletproof argument for biblical creation. We got that on DVD as well. Understanding Genesis, how to defend the 6 days of creation. We have that on DVD as well. Taking Back Astronomy, how the universe declares God's glory, not a big bang or billions of years. Astronomy Reveals Creation, along the same lines, but it's a DVD presentation. Worlds of Creation is kind of what I did in the first session. I never do that exactly the same way twice because it's just, I don't have any notes for that. I just kind of go through and talk about what's cool. Stargazer's Guide to the Night Sky, how to better enjoy the night sky from a Christian perspective. That's just a lot of fun. That's a great resource. Created Cosmos takes you on a tour of the universe from a biblical perspective. His Star, we got Christmas coming up. If you ever wondered about the star that guided the Magi to Christ, this goes into an analysis of that. And I know there's another one that's produced by a lawyer. I think he's wrong. If you want to see why, get the DVD. I did Dinosaurs in the Bible last night, those of you that are interested in that. Keeping Faith in an Age of Reason answers over 400 alleged Bible contradictions and shows they're not really contradictions at all. Discerning Truth, how to spot logical fallacies and arguments that evolutionists make. If you want to get a little better at thinking, Introduction to Logic, which most adults have never been taught, and that explains why most people are not very rational. But if you want to be not so easily fooled by claims that are made, learn how to think. And this book is unique because it shows that logic stems from the mind of God, and therefore the very existence of logic is a proof of the biblical God, a proof of Christianity. And so that's pretty neat. And then we have a teacher's guide to that as well. Secret Code of Creation. I think I'm going to swap out and do this presentation next. I think you'll really get a kick out of that. And we have a book on it called Fractals, the Secret Code of Creation. So you can get the best of our books together for a 20% discount, the best of our DVDs for 20% discount, the best of everything, our library pack for a 30% discount. We only do that here. So the individual resources you can get on the website. The packs only here. So feel free to sign up for our free monthly newsletter. Just put your email address, or you'll get nothing. And then do check us out on the web as well at Biblical Science Institute. Why don't we take a 10-minute break, and then I'll do the final session after that. So thank you very much. All right, let's go ahead and get started. Why don't you make your way back to your seats? We'll do our final presentation here. So I was going to do ultimate proof, but I think you'll like this one better. So secret code of creation. You need a little more pep on a Monday, so we're going to do this one instead because this is fascinating to me. So, I mean, there was the movie National Treasure where they found a hidden code on the back of the Declaration of Independence, and that was kind of a fun movie. And that implied that there was some really intelligent people that put that code back there, right? So, what if we found a secret code like that built into numbers like 1, 2, 3, 4? What if there was a secret code embedded in them somehow? What would that mean? It would apparently mean the creator of numbers is highly intelligent, and we'll see that this code is it's an incredible beauty. It's wild. This is something that was discovered in the 1980s actually, and it's just amazing what you're going to see today. But before we do that, we got some background work to do. It's kind of like, when I was a little kid, and my mother's an amazing cook, but occasionally she would make something I don't like broccoli. Yuck, right? And the rule was you had to eat everything on your plate before you were excused. And so in rare moments of maturity, I would eat the broccoli first, kind of get that out of the way so that I could then enjoy the rest of the meal. You know what I'm talking about? Yeah. So in that same spirit, we got some broccoli to do first, but stay with me because this is going to get really cool. This one's going to blow your minds, okay? But we have to start with some little bit of background work. But again, stay with me. We're going to start with sets. A set is a collection of elements with a common defined property. And so we're talking about sets of numbers. So a set of numbers is a group of numbers that has something in common. And in most sets, some numbers are included, other numbers are excluded. For example, it's pretty easy. Consider the set of even numbers. That would include these ones, right? And it would exclude the other ones. So that's the set of even numbers. That's pretty easy. Now, if we had a different set, let's say the set of negative numbers. Well, that would include these ones, but it would exclude all the others, right? And there's some overlap. -2 is both a negative number and it's an even number, right? Now, with these two sets, you can tell just by looking at the number whether or not it belongs to the set, yes? If it's got a little negative sign in front of it, it belongs. The set of even numbers, you just have to know if it ends in 0, 2, 4, 6, 8, and it belongs. We're going to look at a set that's a little bit more complicated. It requires you to do a little bit of work to figure out if the number belongs because of the way the set is defined. We're going to look at what's called the Mandelbrot set. Interesting. The Mandelbrot set is a set of all numbers, C. C is a potential Mandelbrot number, for which the sequence z sub n remains small according to this little formula. That may sound very complicated, but basically this little formula right here, you watching this? We're going to check to see if C belongs to the Mandelbrot set by putting in that little formula, and then we'll get another set of numbers, Z, that will either remain small or it'll get very big. Those are the two possibilities, okay? So we're going to end up with a sequence of numbers, and if the sequence of numbers remains small, then C is part of the Mandelbrot set. If the sequence of numbers Z gets big, then C is not part of the Mandelbrot set. And the best way to do this is to do a couple of examples. It's not hard. So, is the number 1 part of the Mandelbrot set? So C is 1. That's the number we're testing to see if it belongs, okay? We have Z squared. And by the n just means that there's several z's. There's Z1, there's Z2, Z3, Z4, and each one of them is a little mailbox containing a number. Okay? And so the first Z always starts as 0 by definition. So we have Z, so our first iteration is 0 squared plus 1, which is 1. Yes. Not hard. I know it's Monday, but hang in there, all right? So that's our next value of Z. Now we take that and put that back in. That's the new value of Z. So now we have 1 squared. 1 times itself is 1. Plus 1 is 2. Right. So we put that back in. 2 squared is 4 plus 1 is 5. Okay, so that's our new value. Put that back in. 5 squared, 25 plus 1 is 26. Right, put it back in, 26 squared plus 1 is, it gets getting a little harder, isn't it? But we don't have to do any more because can you see what's happening? Is the sequence of z staying small? No, it's getting big, isn't it? And you can see it's going to continue to get bigger and bigger. So is the number 1 part of the Mandelbrot set? The answer is no, because the sequence of z is staying small, or the sequence of z is getting big. If it has to stay small to be a member of the Mandelbrot set. You following that? Do one more example. I know it's a little tedious. Let's try -1. Is the number -1 part of the Mandelbrot set? So now we have z squared minus 1 is the new value of z, right? So z always starts as 0. So we have 0 squared is 0, minus 1 is -1, right? We put that back in. -1 squared would be +1, minus 1 is 0. Well, that's familiar. Put that back in. 0 squared minus 1, -1. You see what's happening there? 0, -1, 0, -1, 0, negative. And it's going to do that forever, isn't it? Is the sequence of z staying small? Yeah. Therefore, is -1 part of the Mandelbrot set? Yes. Okay, you got it? Now there's one more complication, and then it's going to get incredibly cool, and it's going to blow your mind. Okay? The Mandelbrot set also includes what we call complex and imaginary numbers. So an imaginary number, and I hate the terminology because imaginary makes it sound like it's something we just made up or it doesn't really exist. No, these numbers do exist. They're not made up. But an imaginary number is a number that when you square it, when you multiply it by itself, you get a negative number. And sort of the prototype imaginary number is abbreviated by a lowercase letter I. And by definition, I squared equals -1, okay? And it kind of bothers us a little bit. How can you have a number that when you square it, you get a negative? Because imaginary numbers are not positive, right? Because positive numbers, when you square them, you get a positive. And imaginary numbers are not negative because a negative number, when you square it, you also get a positive, right? And imaginary numbers are not 0 because when you square 0, you get 0. So how do we, apparently an imaginary number, it's not positive, it's not negative, and it's not 0. How do we make sense of that? It's a little tricky. But if you think about it, when you were a little kid, even negative numbers might have bothered you, right? You can say, I can see how I can have 2 apples or 3 apples or 4 apples, but how do you have -3 apples? That doesn't make any sense, right? When you're a kid, negative numbers bother you because you don't have a lot of experience with it. But then you get a little older and you get a bank account, suddenly negative numbers make a lot of sense, right? It's the same way with the imaginary numbers. It's just that most adults never have a lot of experience with them. But there is a class of numbers that's not positive, not negative, and not 0. And these are the so-called imaginary numbers. How do we think of that? Well, here's a number line. The positive numbers you can think of as being to the right of 0, right? The negative numbers you can think of as being left of 0. Where would you put an imaginary number? How about up here? You see, it's not positive, it's not to the right of 0. It's not negative, it's not to the left of 0. And it's not 0 because it's way up there. You can think of the imaginary numbers as being along a different axis. Oh, that's a nice way to think about them. Okay? And you can multiply I, which is the square root of -1, by any so-called real number, half I, negative half I, and so on, and you can get any number along that axis. Okay, so those are all the imaginary, they're all the so-called real numbers. And again, I hate the name, right? Real numbers versus imaginary, but they all exist. The so-called real numbers are along that axis, the imaginary numbers are along that axis, and you can also have numbers that are off axis. You can they can have a real part and an imaginary part, okay? 1 plus a half I, and we call these complex numbers. So complex numbers have a real component and an imaginary component, and we usually plot them so that the real component is the x position and the y is the imaginary. Okay? You following? You following? Okay. So the Mandelbrot set also includes these numbers. And you know how to do it now, right? You run the number through that little formula, and if it stays small, it belongs, and if the z gets big, it does not belong. So we're going to do that. We're going to have the computer do it, though, and we're going to make a map, because The weird thing about the Mandelbrot set is you can't tell just by looking at the number. Remember we looked at 1, the number 1, and we found it did not belong to the Mandelbrot set, but -1 does belong. You can't tell just by looking at a number. And so I want to know if there's a pattern. Is there any kind of, is it just all chaotic, or is there actually a pattern there? So we're going to make a map of the Mandelbrot set. Okay? And we're going to have the computer do it, because computers are very happy to do calculations repeatedly, and they can do it very quickly. And what we'll do is we'll have the computer run it through that little formula, and if Z stays small, it's part of the Mandelbrot set, we'll color it black. So we checked, remember we checked -1, and it went 0, -1, 0, negative, so it stayed small. If we'd have checked 0, we'd have found it also belongs to the Mandelbrot set. So we'll color those points black, and we'll have the computer check other numbers, and we'll find that all of these points do belong to the Mandelbrot set. Looks like there might be a pattern, huh? Points that don't belong, we'll give some other color, like red. Remember we checked 1, the number 1, and we found that, 1, 2, 5, 26, and it just gets really big really fast. And we'll have the computer check other points, and we find these ones don't belong. Interesting. And as we check more and more points, a pattern emerges. And the shape that emerges was not something that anyone was expecting. The shape that emerges is this. This is a map of points that belong to the Mandelbrot set in black. Now, points that don't belong, I colored them red if the sequence of Z gets really big really fast so that they're far away from the Mandelbrot set, dark red. Brighter and brighter if they're close to the Mandelbrot set, and yellow if they're really close but they're still off. The Z gets big, but it does so very slowly, okay? So what you're looking at now is a map of the Mandelbrot set. So now we don't have to go through that formula. The computer's already done it. So now I can just look at the map, and I can say, does 1/2 I belong to the Mandelbrot set? Yes, it does, because it's black, right? Does 1 and 1/2 belong? No, it doesn't, because that's a red point. So that does not belong. So now we have a convenient map. I'm going to remove the number line so you can see the shape a little better. It's a very interesting shape, and it's made up of smaller shapes. It's made up of this large heart structure. That's called a cardioid. A cardioid, because it's like a heart. And it is exactly the shape that is made when you roll a circle around another circle, keeping your pencil affixed to one point on the moving circle. See? That's a cardioid. And that's exactly the shape that the main part of the Mandelbrot set makes. Cardioid. Pretty neat, huh? The other shapes are circles. You see these circles, and they're perfect circles growing off the cardioid. And then there's circles growing off of them, and so on. And then the other feature you find are these little antennae that sort of grow off, these little wire-like structures. Very strange. We can zoom in on sections of the Mandelbrot set by having the computer plot finer and finer points. We can zoom in on this upper section, for example. And the cool thing here is you find that you see the antennae here? How there's 3 of them, right? Because you got the trunk and then you got 2 stems, so for a total of 3. Now if you look at the next one, it's 1, 2, 3, 4, 5. The next one, they're getting smaller. 1, 2, 3, 4, 5, 6, 7, 9, 11, 13, 15, 17. Interesting. There's a pattern there. These little antennae that grow off, each one has 2 more than the previous one. It's kind of wild. All the way down. And by the way, they never stop. They get smaller and smaller and smaller, but they never stop. There's an infinite number of these. So they go all the way down to infinity. Odd infinity, for whatever that means. On the other side, on the right side, this one is 1, 2, 3, 4, 5, 6, 7. So you have all the numbers on the other side. All the odd numbers on the left, all the numbers on the right, starting with 3. And then it gets even cooler, because if you take 3, this one has 3 and that one has 5, and you add 3 and 5, you get 8. Lo and behold, that's exactly how many this has. And that's true for all of them. You take any 2 large points and you look at the next largest one in between them, and it adds the number of antennae. That's true for all of them, no matter how small you go. Amazing. So it's somehow remember, all we're looking at is a map of which points belong to that little formula. That when you run them through there, the sequence of Z stays small. And this is the shape that you get, and somehow it knows how to count. It knows how to count by odd numbers or by all numbers, and it knows how to add. Pretty remarkable. Nobody was expecting this kind of map to be built into the numbers. Really strange. So One of the other really neat things about the Mandelbrot set we're going to look at now, so you have, kind of keep in mind the main shape, right? You got the cardioid, you got the main disk, and you got these other smaller circles, and you got this little tail out here. And you might notice on this tail, there's a little bump right there. Let's zoom in on that and see what that is, which we can have the computer do. And it turns out it's a baby Mandelbrot set. That's kind of wild. Nobody was expecting that. It's got the same cardioid shape. It's got the same discs growing off of it. The only difference is it's got some extra spikes growing off of it that were not on the main one. We zoomed in on the spike of the main Mandelbrot, and the baby version had extra spikes. Is that a coincidence? And we notice it also has a tail, and it's got a little bump on it. What could that possibly be? Oh, it's another one. I told you this was mind-blowing. And, of course, now we have spikes, and we have spikes growing off of spikes. And, of course, on its tail, it's got another one. Yeah. Apparently, you could do this forever. There are an infinite number of babies, each one growing off the tail of the baby before it. Gives you a little window into the mind of God. Because you see, it's my contention that God's mind is responsible for numbers. We didn't create numbers. God did. We discover them. And this map that has existed, it's been built into math since eternity past, is infinitely complex because it's got little baby versions built into it. And the stuff on the exterior that grows off of it, spikes upon spikes, it gets increasingly beautiful the more you zoom in. They get prettier and prettier as you zoom in, really made. So look how small this is compared to the original. Just a little window into the infinite mind of God. And in case you're wondering, there's no bigger version. This is the atom of the Mandelbrot set. If you could zoom out, there's nothing beyond it. So that tendency of something to have smaller versions of itself built in, that's called a fractal. So this is an example of a fractal. And it's not just the overall shape that repeats. You can zoom in on kind of any section of it, and you think, well, it's going to end at some point, but it just never does. It turns out it's infinitely complex, the shape, and so no matter what section you zoom in on, it will continue to go on forever and ever and ever. It's rather hypnotic, really. So that gives you, again, a little window into the mind of God, who has all this in his mind, and we can explore just a little bit of it. You could do that forever. I mean, it goes on infinitely because it's math. One of the cool places to explore, and I found that the valleys, like you see this valley right here, any place where two shapes kind of come together is a good place to explore. You get really pretty stuff there. And so the first place we're going to look at, it's called the Valley of the Seahorses. Mathematicians like to give fun names to the different regions of the Mandelbrot set, because if you look over on the right side, it looks like upside-down seahorses, right? And by the way, the colors are arbitrary. By convention, points that do belong to the Mandelbrot set are colored black. Points that are not are colored some other color. We can change that from time to time just to keep things interesting. So there we go. And then let's zoom in on one of those seahorses. I want to see what that looks like. Okay, I need to explain what's happening here. Remember, this is just a map of which points belong to that formula, where z stays small when you run it through the formula. Black means they do belong, colored means they don't. Bright color means they're very close. And yet, you say, well, this doesn't look like it's close at all to that, right? What's happening here is there's actually a very thin black thread that comes out and wiggles around and branches. It's just so small, it's smaller than a pixel on the computer. So this really is very close to points that are on the Mandelbrot set. It's just a very thin thread that's winding around there. It turns out it's an infinitely wiggly thread. When you zoom in on it, it continues to wiggle no matter what scale. So that's pretty wild. So I wanted to zoom in on the center of that seahorse and see what that's made of, and you find this sort of spiderweb type structure. That's kind of neat. Now I found from experience, you can zoom in on the middle of that your entire life, and it never ends. It just gets smaller and smaller and smaller. So I thought, I'm going to zoom in on the threads and see what they're made of. So here we go. Quite beautiful, really. They're made up of smaller spiderweb threads. Let's pick one of these in particular. There you have sort of two central hubs. There's a hub there and a hub there. And they kind of collide in the middle, and then there's 4. 1, 2, 3, 4. And you'll find as we zoom in, it'll go from 4 to 8, 16, 32, 64, 128. It multiplies by 2. It's all the powers of 2 our equation is z squared. Might that have something to do with it? Let's zoom in on the middle there. So you can see it going from 4 to 8 to 16, and in the middle, lo and behold, it's another baby Mandelbrot. Isn't that interesting? Yeah. And it's rotated a little bit. We zoomed in on a spider web that's twisted a little bit, so it's rotated around. And around the exterior, we find all kinds of spider web structures because we zoomed in on a spider web, and the baby version has extra spider webs growing around it. Now, the interesting thing about this one is it also has a little baby on its tail, which has a baby forever. So the Mandelbrot set not only has an infinite number of babies, each baby has an infinite number of babies. It's an infinity of infinities. That'll keep you awake at night, right? So God's mind is not just infinite, it's infinitely infinite. Does your head hurt yet? Look how small this is compared to the overall shape as we zoom back out. It's kind of amazing. There are an infinite number of those in the Mandelbrot, so pretty wild. Okay, so let's go back into that same valley, but we went off to the right last time. This time let's go off to the left into the valley of the double spirals. And we'll see what these things look like. I love these things. They remind me of spiral galaxies, actually. But what you have here is, it's a double spiral because it's two strands that wrap around each other. You see that? There's this strand right here is the same as this one, but you can see there's a strand in between. That one right there that goes out that way. Oops, let me back up. Sorry, hit the button. Okay, so now I found again, you can zoom into the center on that forever and it spirals inward infinitely. So we're going to go off to the side and we get these incredibly beautiful structures. Again, you're looking at a map of which numbers belong to that little formula. And it turns out that it's remarkably complex and beautiful. Who would have imagined that such beauty would be built into numbers by the creator of numbers? But then we think about it, we think, well, God does have a sense of beauty. And God's mind is responsible for numbers and the laws of mathematics, right? So, yeah, of course you're going to find beauty in math. It makes sense. There's a new structure here. I call them bow ties because they look like a little bow tie. You see that? Two little double spirals that intersect in the middle. I find them incredibly beautiful. Isn't that nice? And again, you have 1, 2, and then you have 4 there, and then 16, or then 8, 16, 32, and so on. And in the middle, again, you have another little baby version. Isn't that lovely? And it's surrounded by all these beautiful double spirals because we zoomed in on that. So did any of you know that math contained that level of beauty? Because before 1980, nobody did. Benoit Mandelbrot, the set's named after him. He was a math guy who worked at IBM. And right around the time computers were getting fast enough to plot these things efficiently, he started popularizing this. But pretty remarkable that this was built into numbers, those numbers that you learn in grade school, 2 plus 2 equals 4, and so on. It turns out there's beauty built into them. Incredible beauty. So another place we can zoom in is we call it the Valley of the Elephants. That's if we zoom in on the main cardioid here, that heart shape. This is the only symmetric valley where they're identical they're like a mirror reflection of each other. And Valley of the Elephants, because it looks like a bunch of elephants marching along, one after the next. Isn't that neat? And their trunk kind of curls up. Each elephant is standing on one circle, right? Well, it's a circle on a circle on a circle, but there's each elephant, one circle. They go on infinitely. As you go deeper into the valley, the elephants get smaller, their trunks get curlier, but they never end. There's an infinite number of elephants there. Let's zoom in on one or two of them. So there you go. One elephant standing on one circle, like a circus elephant balancing on a ball. I don't know, it's kind of wild. And if we zoom in on the trunk is a single spiral, not a double. So a single spiral means there's only one strand, right? So there it goes. You can zoom in on the center of that for the rest of your life. It never ends. So let's go off axis into one of these threads and find out what they're made of. Interesting. Quite beautiful. Zoom in a little more. You find the bow tie structures again. This time they're made out of single spirals rather than double, which is interesting because we zoomed in on a single spiral. And there they go. Look at that. And then it goes from 2 to 4 to 8 to 16 and so on. And in the middle, again, you got a little baby Mandelbrot right in the middle. Isn't that amazing? Yeah. It gives you a little window. This is the mind of God that we're looking at here, just the way God thinks about numbers. And it's beautiful, isn't it? God does have a sense of beauty. Math not only is efficient and allows us to send probes into space and so on, but it's remarkably beautiful. So all of that's just a map of which numbers belong to z squared plus c when you run them through the formula, where z stays small. And that made me think, what happens if you change the formula? Because frankly, this shape is infinite. You could zoom in on this forever. It doesn't end. It goes on infinitely. And you, by the way, if you want to, you can like Google Mandelbrot deep zoom, where they zoom in by a factor of like a Google. And it just keeps going. Supercomputers can do that. So you could spend the rest of your life exploring this shape. It's infinite. You'd never exhaust the riches of its beauty. But then that made me wonder, what happens if you change the formula? Now I found if you change c, like half c or twice c or c times I, all it does is expand or shrink or rotate the shape or move it. But what happens if you change the power of z? So I thought, let's try z cubed. Do you get a fractal? Here's the shape you get with z cubed. It's a different shape. Interesting. And so let's have a look at this one. The other thing we can do too is I can have the computer do not just 2 and 3. I could do 2.01, 2.02, 2.03, and step it up to 3. We'll do that here in a moment. But the main shape here is a nephroid. A nephroid's where you take a circle half the size of the original and roll it around, keeping your pencil affixed to one point on that. And that's exactly the shape you see on this new shape. Okay, this is sometimes called a multibrot. The original was the Mandelbrot. This is a multiple of it, so a multibrot. And so what I'm going to do now is step up the power from 2 to 3 gradually, and so you can see one shape kind of morph into the other. It's kind of fascinating to watch this. Isn't that neat? And what happens here is interesting. Everything kind of goes up by 1. So in the original Mandelbrot set, you have the cardioid. The cardioid has one valley in it, this one right here, and circles which have no valleys. The nephroid has 2 valleys. It's got one there and one there, and instead of circles, it's surrounded by cardioids, which have 1 valley. So the number of valleys on everything is increased by 1. The little baby Mandelbrot, it gets multiplied by 4 actually, but most things either get doubled or they go up by 4. So is this shape fractal? Well, actually, let me ask this question: which section is least changed when we go from the Mandelbrot to the first multibrot? What part is least affected? I think the right side. Yeah, I think like over here. The left side's changing like mad, the right side not so much. So that made me wonder if this has a Valley of Elephants. And it turns out it does. But there's a difference. Yeah, that's right. They've doubled. Because remember, before, each circle had 1 elephant, but the circles have become cardioids, and now there's 2 elephants on each one. The number of elephants have doubled, which is interesting because originally we had an infinite number of elephants, and now we have twice that many. Think about that for a while. God's not just infinite, he's infinitely infinite. So what happens if we zoom in on the trunks of these guys? You get single spirals again. Do you think we'll have the little bow ties like we had before? Let's see. 3, yeah. So instead of having just little 2, they've got 3. It looks like a fidget spinner. That's exactly what it looks like to me. And in the middle of our little fidget spinner is the overall shape. So it's a baby multibrot. So it is fractal. And you can see it's nearly identical to the original. It's just got extra spirals growing on the outside. So this is also fractal. Pretty neat. And so now I want to try. So you could spend the rest of your life exploring this shape. It goes on infinitely. You would never exhaust its riches. It goes on forever. So it made me wonder what happens if you try other powers. So this is e to the 3rd power, z cubed. And it has kind of a twofold shape, right? It's like a mirror is right here, and it's reflected that way and that way. It's got 2 large cardioids. Z to the fourth has 3. 1, 2, 3. You see the pattern? The next one has 4. 1, 2, 3, 4. Each one, and they gain valleys, right? So apparently it's the power minus 1. So 5 minus 1 is 4, 4. Z to the sixth, 5-fold symmetry. And Z to the seventh, snowflakes. And if you zoom in on this, do you get baby snowflakes? You sure do. You sure do. So it's fractal as well. Isn't that neat? Then I thought, what happens if you try negative powers? Negative powers are very interesting. So this is e to the negative 2. Now, negative power, that's the reciprocal of the positive power. So this is 1 over z squared. Now remember, black means it does belong. Colored means it doesn't. It flips it inside out. Because now, these are all black. Most of the universe is part of this set, except for a little section in the middle. Okay, so it kind of flips the thing inside out, which I think is neat. Is it fractal? Let's zoom in on a section of it. And the negative powered ones are very different. They have this kind of pebble-like structure. Remarkably beautiful. You can see the pebbles are not totally random. They have kind of a pattern there. And if we zoom in on it, you see that even though the overall shape doesn't repeat, because it's inside out, it can't. But nonetheless, it goes on forever. So it does have that fractal nature to it. Isn't that wonderful? Again, just gives you a little window into the mind of God who thought of all this. All this is in his mind, and that's why we can analyze it. So there's z to the negative 2, z to the negative 3 gets you this, z to the negative 4 gets you that, z to the negative 5, another way to make snowflakes, inside-out snowflakes. So there you go. So isn't that neat? Kind of amazing. And it's just amazing the beauty you can find in these things. It's quite wonderful. So, artwork of God built into numbers from eternity past, and yet we only discovered them in the 80s. So what does all this mean? I mean, it is, it's a cool background, but aside from that, is there any use to these? What causes the beauty in fractals? What causes the complexity in fractals? Why do they have these amazing shapes? Why are they so beautiful? First question, what causes the beauty? What causes these shapes to be beautiful? Is it the man-made color scheme? Now, I picked the colors, right? By convention, parts of the Mandelbrot set that belong are black, but then I picked the exterior colors. There are some programs that pick horrible color schemes, and shame on them. I picked the colors, but you know what? That's not really causing the beauty, because even if we took away the colors, still beautiful. There's something about this shape that's very attractive to the mind. We look at it and we say, there's beauty there. Now, I think the color adds to it, maybe the same way that salt kind of brings out the flavor of the food, makes it taste a little better, but it doesn't create the food or the flavor. And frankly, the colors belong to God anyway. I just picked which ones go with which. So it's not the man-made color scheme. That's not what causes the beauty. Did the computer create this beauty? Some people think, well, yeah, the computer created these fractals. No, it didn't. No, it didn't. It was able to analyze them rapidly. But remember the first 2 points, -1 and 1, we checked those manually, right? And we could, theoretically, you could do this all by hand. It would just be incredibly tedious. But you could analyze and see how fast Z escapes and give it a different color. You'd end up with the same shape. The computer didn't create it. The computer simply revealed it quickly. Did people make this? Well, it's infinite. No human being could make something like that. We certainly appreciate the beauty, don't we? But we didn't create it. Not at all. In fact, people were surprised that this thing was built in, that the map of the Mandelbrot set would look like that. We were astonished at that when we found that that's what it looks like. You wouldn't be surprised by something you made. And frankly, nobody could. Nobody could say, you know what, I'm going to make a heart shape and then I'm going to draw an infinite number of circles. Well, that would take the rest of your life. You can't do that, and then some. The beauty is apparently built into math. Interesting. What causes the complexity in fractals? The fact that, they can add and you find the powers of 2, 2 goes to 4 to 8 and so on. Did the computer create it? Obviously not, because again, we plotted the first couple points manually. The computer simply revealed it quickly. Computers don't create these fractals any more than microscopes create bacteria. Microscopes allow you to examine bacteria and see details that you can't see with your naked eye. Likewise, the computer allows us to examine these maps quickly, something that you could do by hand. It would just take forever. Did human beings create it? Again, no. We were surprised to find these incredible mathematical properties. Nobody sat down and decided that The Mandelbrot set will have antennae that branch into 3, then 5, then 7, and so on. It's just the way it is. And we were surprised to find that. Did the formula create it? Well, we ran the numbers through that formula to see if they belong, and we get to define the formula. But what we found is it doesn't really matter too much what formula you use. You go z cubed or z to the 4th, you still get fractals. So the formula just, it's relevant, it determines the exact shape, but it's also the properties of numbers that you run through that formula that determines the shape. Apparently, the complexity is built into math. So, what is math? Well, the definition is it's the study of the relationship between numbers. Okay. What are numbers? I mean, it seems silly to ask that question. We know what numbers are. But have you ever tried to define what a number is? It's kind of interesting. I looked through a number of dictionaries. About the best definition I could find of numbers are that numbers are a concept of quantity. When you think, so a concept is something that exists in your mind, right? So when you think about the amount of something, that's a number. Okay, so when there's 12 oranges. 12 is the number, it's a concept. The oranges themselves are not a number. What I'm thinking is. Numbers are concepts. They're abstract in nature, not physical. They exist in the mind. Now, you say, well, I don't know. There's the number 3. That doesn't exist in my mind. It's right there on the screen, right? But is that really the number 3? Because if it is, I just destroyed the number 3. Students will now have to count 1, 2, 4, and so on. All right, no. That wasn't really the number 3. That was a written representation of the number 3. That was a numeral, right? Written numerals are not numbers, they're representations of numbers. So I can write down a 3 that represents the concept of 3-ness, but then if I destroy the symbol, it doesn't destroy the number. Numbers are conceptual. Get this, numbers exist in the mind, okay? Laws of math are conceptual, they exist in the mind. 2 + 2 = 4. That's a conceptual principle, it exists in your mind. Where do laws of math come from? Did they evolve? In biology, the way evolutionists like to explain the complexity of living creatures is, well, they didn't start that way. They started very simple, and then over time they evolved. Was the Mandelbrot like that? Did it start very simple and then it evolved? And the answer is no, because numbers don't evolve. It's not like 7 used to be 3, but then it evolved, right? Numbers always are what they are. And the relationships between them don't change. It's not like 2 + 2 used to equal 3 and then it evolved to where it equaled 4. No. So you see the evolutionary explanation, that doesn't work for math. You cannot account for laws of math in any kind of evolutionary scenario. It don't work. There are no evolutionary mathematicians. There are evolutionary biologists. There are no evolutionary mathematicians. If you had an architect who believed in evolutionary math, don't hire him. That's not going to work. Were laws of math created by people? No, they were discovered by people. It's not like, triangles didn't add up to 180 degrees before people decided they should, or that the sum of the squares of the 2 legs of a right triangle equaling the square of the hypotenuse. Pythagoras didn't make that happen. He just discovered a new way to prove it. They weren't created by people. Do they come from the universe? Some people think so. But laws of math actually go beyond the universe. Now, the universe does obey math. There's no doubt about that. That's a separate question. But math doesn't come from the universe. Math goes beyond the universe. Our universe has 3 dimensions of space, 1 of time. But in math, you can have any number of dimensions, 6, 7, infinity. There's a thing called Hilbert space where you have an infinite number of dimensions. And it's mathematically meaningful, and yet it doesn't apply to the physical universe in terms of space anyway, because our universe has only those dimensions. So it's not something that comes from the universe. Laws of math stem from the mind of God. The reason 2 + 2 = 4 is because God wills it to be that way. His thinking is self-consistent, and that's why math is. If you think about it, laws of math, think about the commutative property of multiplication, the fact that A times B = B times A, right? That's a timeless truth. It's something that exists in the mind. It's conceptual. Laws of math are conceptual. They're universal, meaning they work everywhere. They're invariant. They don't change with time. And they're exceptionless. Right? And if you think about it, all that makes sense because God's thoughts are conceptual, because all thoughts are. God's omnipresent, so of course his mind governs the entire universe. Therefore, they'll be universal. God doesn't change with time. right? He says, I, the Lord, do not change, therefore you sons of Jacob are not consumed. And therefore the way God thinks about numbers does not change with time. And God is sovereign, therefore his thinking is exceptionless. There's nothing that's true that's outside the mind of God. So I can account for the existence and properties of laws of mathematics because I'm a Christian. I can make sense of this. I can make sense of why math is the way that it is. Because in the Christian worldview, it would have to be that way. But the naturalist has a problem. So the naturalist is someone who believes that nature's all that there is, right? There's no God, or if there is a God, he's within nature. There's no transcendent God. Everything that exists, matter and energy and so on. He's got a huge problem because on the one hand, he knows that laws of mathematics are conceptual. They exist in the mind. Math is something you do up here, right? On the other hand, laws of math existed before people. The way the planets orbit the sun. Remember, if you were here for the first session, p squared equals a cubed. That expresses the relationship between the period of a planet and its orbital distance from the sun. That worked before human beings discovered it. That worked before human beings existed, for 2 days anyway, and in the evolutionary view for billions of years. Math worked before people were around to discover it. So, how does the naturalist answer this? See, I can answer that. Laws of math require a mind. There was a mind before people, the mind of God. There was a mind before the universe, the mind of God. I can explain why laws of math have always worked and always will. The naturalist can't, because in his view, there aren't minds before people, at least minds capable of doing mathematics. If you understand this is a powerful disproof of the atheistic worldview. It really is. Now, we also have what we might call physical fractals. The fractals we've looked at so far are mathematical graphs. You can't touch them. You could plot it on a computer screen and touch the screen, but the shape itself exists in the world of math. It's abstract. But there are fractals that you can touch that are made up of atoms. And although physical fractals don't repeat forever, because the Mandelbrot set, you can zoom in on it forever. It keeps going. Physical fractals, you can't do it forever. They zoom in to a certain point, and you get to the atoms, and they're not fractal anymore. But nonetheless, the physical world contains many approximate fractals. For example, snowflakes. Snowflakes. And they're quite beautiful when you look at them under a microscope. They are fractal in nature because you zoom in on them, the overall six-fold shape continues. Maybe not exactly, but approximately. And so these little gems from heaven that the Lord sends us from time to time in certain places, quite beautiful and fractal in nature. Wonderful. Stuff that grows on your windows. I don't know if it gets cold enough here for this to happen, but growing up in Ohio, where it's kind of a humid environment, in winter, sometimes you get these beautiful crystalline structures that would grow on your windows from the moisture. And it's because of the shape of the water molecule, they tend to form these fractal shapes. It's delightful, incredibly beautiful, where they branch and branch into branches, and so it has that fractal quality to it. Ferns, the way ferns branch is fractal. Because you have the main stem, and then there are branches that branch off of that, and branches that branch off of the branches, and branches that branch off of the branches of the branches, and so on, to a certain point. They don't go forever, but they go quite a ways. Each leaflet looks kind of like the overall fern. I even found fractal broccoli. So I guess broccoli is good for something after all. There you go. See how it's a cone? And then it's made up of smaller cones, which are made up of smaller cones, which are made up of smaller cones. Pretty remarkable. It's called Romanesco broccoli. It's a real thing. So the way coastlines branch is fractal. Branch and they branch into branches, which branch into branches. The way mountaintops branch. You look at mountains from space, the way the valleys branch is fractal. It really is. So you zoom in on it and it's like a smaller version of the original thing. The way clouds form is fractal. Am I looking at the entire sky or am I zoomed in on one small section of a cloud? It's hard to tell because the small version looks kind of like the overall version. It's called scale invariance. That's a property of fractals. The way lightning branches is fractal. Because there's a main branch, and it branches into smaller branches, which branch into smaller branches, each of which kind of resembles the original. And really rather remarkable, the way that happens. So it is fractal. And you can see it happening with ultra slow motion. You can actually watch the branching occurring. It's pretty remarkable. Isn't that neat? Until the leader connects, and then most of the current goes down the leader. But isn't that neat? That's a fractal in time there. So here's my question then. Why do fractals occur both in math and also in the physical world? Right? Because, that shape right there, that's z to the 7th plus c. That is a mathematical graph that it's not made up of atoms and it doesn't exist in nature. But that does. And they're similar. That right there is part of the Mandelbrot set. It's a mathematical graph. It does not exist in nature, but that does. This may look like a plant. It's actually a mathematical graph. It's called a Barnsley fern. A Barnsley fern is each leaflet of the fern is the entire fern. Let me show you. You can take the entire fern and it becomes one of its own leaflets. See? I'll do that again because it's amazing. Isn't that wild? That is a mathematical graph that does not exist in nature, but that does. That shape, mathematical graph, does not exist in the physical world, but that does. It grows on your windows in certain climates. That is a mathematical graph of cones on cones on cones. It does not exist in the physical world. This, unfortunately, does. That shape is part of the Mandelbrot set. You can't see that anywhere in the physical universe, but this you can. The Whirlpool Galaxy, you can see that in a small telescope if you know where to look. Why? Why? Why do fractals occur both in math and the physical world? Now, one answer would be, well, the physical world obeys math. And that's true as far as it goes, okay? Because why is it that these mathematical graphs resemble things in nature when math's in your mind and nature is made of atoms and is not in your mind? Well, the physical universe obeys math. So it stands to reason that if these shapes can occur in math, they can occur in the physical world, which obeys math. That's a good answer as far as it goes, but then I'm going to have a follow-up question. Why does the physical universe obey math? Now, everybody assumes that it does. If you've had even one class in physics, you know that F equals ma. That's a formula relating the force, the mass, and the acceleration of physical objects. It obeys a mathematical law. But why? Why does it do that? Now, in my worldview, I can make sense of that because math is a reflection of God's thoughts. And whose mind is it that upholds this physical universe? It's God's, right? The mind of Christ in particular. Hebrews 1:3, he upholds all things by the word of his power. So the universe is upheld by the mind of God. God thinks mathematically, right? Therefore, the universe will obey mathematical laws. That has to be the case in the Christian worldview. I can make sense of that. But the secular worldview can't. If you're not a Christian, you cannot make sense of why the physical universe obeys math. Now, you see, but it does. I know it does. But you can't make sense of that. Why does it obey math? Math is something that exists in the mind. Why does the universe feel compelled to obey something that's going on in my mind? That doesn't make any sense. But in the Christian worldview, it does, because my mind is a shallow reflection of the way God thinks, because I'm made in God's image. I have the capacity to think in a finite way, in a way that's consistent with his character. Secular worldview can't answer that. They can't explain the properties of laws of mathematics. Why math? Because mathematics, we said, it's conceptual, it exists in the mind, it's universal, it works everywhere, it's invariant, it doesn't change with time, it's exceptionless. They can't explain any of those or justify them. Why is it that the atheist believes that 2 + 2 = 4 on Mars? It can't be because he's been there, because nobody's been on Mars. And yet we all assume that the laws of math work there, right? And on the moon, and etc. But I, as a Christian, can explain that. I can say, oh, because the God of the Bible, his mind is upholding Mars and the Andromeda Galaxy and Earth and everything else. And so, of course, math is going to work there. But secularists can't answer that. And if you want an example of this, there's a wonderful article written by Dr. Eugene Wigner. Now, he is a physicist, PhD in physics, and a Nobel Prize winner. This guy is brilliant. But apparently he's not a Christian. Because when he tackled this question, he's basically asking the question, why does the universe, which is physical, non-mental, obey math, which is mental? How does that happen? So he writes an article on this subject called The Unreasonable Effectiveness of Mathematics and the Natural Sciences. Why does the universe obey math is the question he's trying to answer. In the article, he says, it is difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and of the human mind's capacity to define them. So he's basically saying there's two things that are amazing. First of all, that the physical universe obeys laws at all. Because from an atheistic perspective, why would it? In a chance universe, why would you have laws that the universe feels compelled to obey? And the other thing is that we're actually capable of discovering what some of these laws are, because they happen to be conveniently mathematical. F equals ma. That's awfully convenient. E equals mc squared. You heard of that one? That's convenient. Why? Here is the conclusion of one of the most brilliant physicists who ever lived, who is not a Christian. The miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. In other words, he doesn't have an answer. He can't explain it. It's just amazing. The universe just happens to obey math. See, from a Christian perspective, I can explain that. I can make sense of it. That's a Christian principle. But he can't make sense of it. And by the way, a wonderful gift, a gift implies a giver. Yeah. Which we neither understand nor deserve. I'd agree with that. We don't deserve it. But we have a God who is gracious and who has organized his universe in a way that we can at least partly understand through cognitive reflection and experimentation and so on. Secularists can't answer that. So we've seen that beauty of infinite complexity is built into numbers by the creator of numbers. Numbers are abstract conceptions of quantity. They exist in the mind. Concepts require a mind. Numbers are a reflection of the way God thinks. What we've been doing today really is theology. We've been seeing how God thinks when it comes to numbers, and we've seen that the results are beautiful. God has a sense of beauty, and he's built that into mathematics. It's wonderful. I hope you get that. That's the main point. Even if you got lost in some of the details, the main point is that math makes sense because it stems from the mind of God. The secular worldview cannot account for the existence and properties of numbers or mathematical truths. Numbers existed before people, yet they are conceptions, meaning they require a mind. That's not a problem for the Christian because we have minds before people, the mind of God. The secularist has a huge problem because he doesn't have minds capable of thinking mathematically before people, and yet math worked before people. Laws of mathematics are universal, invariant, abstract entities, and we can account for that because of the biblical God and the way he thinks. Now, the physical world also contains fractals, and we can make sense of that in the Christian worldview. The secular worldview can't make sense of that. Why the physical universe obeys mathematics? One of the most brilliant PhD Nobel Prize-winning physicists could not answer that question and wrote an article admitting that after having given it tremendous thought. And nobody else has been able to do any better. The universe is controlled by the mind of God. That's why it obeys math. When you study math, you are learning to think about numbers the way God does. You won't be able to do it infinitely like he does, but you're training your mind to think in a more godly fashion. That's pretty neat. That's pretty neat. And you can explain why the universe obeys math because it's the mind of God that upholds that. This presentation, we have that available on DVD in the back if you'd like to kind of review some of that stuff. We have a Blu-ray of it as well because it's really very pretty. And then we have a book on this topic as well called Secret Code of Creation. And if you get the book, you also get software that will allow you to explore these shapes on your own computer. Pretty neat. And it's just a beautiful resource and a lot of fun. Ultimate Proof of Creation, if you want a bulletproof argument for biblical creation, that's the book you're going to want to get. There's a DVD along the same lines. Understanding Genesis, what I talked about Sunday morning, and how to defend the literal time scale of Genesis. And that's on DVD as well. Discerning Truth, how to spot the top 10 fallacies that evolutionists commit in their reasoning. Created Cosmos, Tour of the Universe from a biblical perspective. Stargazer's Guide to the Night Sky, how to better enjoy the night sky from a Christian perspective. Taking Back Astronomy, how to refute the Big Bang in the billions of years from evidence in outer space. A lot of good stuff there. Astronomy Reveals Creation would be the DVD that would go along with that. I won't go through all these, but remember the packs as well. You can get those if you want to get a tremendous discount on things. Don't forget to sign up for our monthly newsletter. And we just want to bless you with that. But be sure to put your email address and do so legibly because we have to enter these things in. And do check us out on the web as well at biblicalscienceinstitute.com. Thank you very much. God bless.
High school needs to go to For everyone else, thank you for coming.